Hello, and welcome to Night Cosmos Sleep, where the deepest stories of the universe are told in a slow and peaceful rhythm. Out there, galaxies continue drifting quietly through the darkness. Stars are still burning, while ancient light keeps traveling across space just as it has for billions of years. But what if one day, new measurements revealed that the familiar story of the universe's beginning had never truly been complete? The universe would not suddenly stop. No stars would disappear, and there would be no second explosion. Only the place of the Big Bang within cosmic history would change. It might no longer be the first page, but simply the earliest boundary humanity is currently able to see. Beyond that boundary, there may have been a universe that once contracted, a cycle that ended long ago, or a state in which space and time had not yet taken on their familiar forms. Tonight, we will gently follow the traces that remain to explore what may have existed before the Big Bang, and how the story of the universe might change if its true beginning lies deeper than humanity once imagined. When people hear the words Big Bang, many imagine a violent moment. A tiny point of light suddenly exploding in the middle of dark, empty space, and hurling stars, planets, and galaxies in every direction. That image appears in illustrated books, documentaries, and familiar simulations because it is simple, powerful, and easy to remember. But the universe described by science did not begin like a bomb exploding inside an empty room. A bomb always has a location. It explodes at a specific place, after which matter flies outward from the center and expands into space that already exists around it. The Big Bang does not have that structure. There is no point between the galaxies that we can identify and say everything was once launched from there. Nor was there an empty dark region already waiting outside for the matter of the universe to spread into. What is expanding is not merely galaxies moving through space. The spatial distance between very distant galaxies is itself increasing. We can imagine a very large sheet of soft fabric covered with many small dots. Each dot represents a galaxy. When the fabric is stretched evenly, the dots do not need to crawl across its surface, yet the distances between them still grow. From the position of any one dot, most of the others appear to be moving away. A distant dot separates faster than a nearby one, simply because more expanding fabric lies between them. In this image, no dot needs to serve as the center. Every location can observe a similar picture. The fabric analogy helps us imagine only part of the phenomenon. The universe is not necessarily a thin surface being stretched inside a larger room. The fabric in the example has edges, an upper side, and a lower side, while real space may have none of those features. What matters is the general behavior. Distances between widely separated regions can increase without everything having to fly outward from a central point. Even the phrase, "the universe is expanding," can sometimes make it seem as though it must be expanding into something. But expansion does not necessarily require an empty region outside. Distances can change within the structure of space itself, much as every square in a grid can become wider at the same time. No additional corridor outside the grid is required to give the squares room to expand. This also means the Big Bang did not occur in some distant corner of the universe. If we trace the expansion backward into the past, every region of space we see today was once closer together. The place where Earth now exists, the location of a distant shining galaxy, and even the enormous empty regions between galaxy clusters were all parts of the same ancient state. In that sense, the Big Bang did not happen at one particular location. It involved all of observable space. Today, many galaxies are separated by dark distances so vast that light takes an immense amount of time to travel between them. But if we could run the film of the universe backward, those distances would gradually shrink. Galaxy clusters would move closer together. The cosmic web of matter would become more tightly packed. Gas, radiation, and particles would be compressed into an increasingly dense state. The farther back we go, the higher the average temperature of the universe becomes. One way to imagine this is to think of light being stretched along with space. As space expands, the wavelengths of light become longer and their energy decreases. Reverse that process, and light in the past had shorter wavelengths and carried more energy. The universe was not only smaller in the sense that its regions were closer together, it was also far hotter. Matter did not exist in its familiar forms. There were no planets and no stars, and during sufficiently early periods, even complete atoms could not yet form. The environment was so hot that the components of atoms moved freely through a dense sea of matter and radiation. Light could not travel great distances as it does today because it was constantly colliding with electrically charged particles. The Big Bang, in the sense most clearly supported by observation, is the story of how that hot, dense state expanded, cooled, and gradually produced increasingly complex structures. When the temperature fell far enough, the first atomic nuclei could remain stable. Later, electrons joined nuclei to form atoms. Gas began gathering under gravity. The first stars ignited, galaxies formed, and over immense spans of time, matter within some star systems created planets, oceans, and the elements required for life. This entire process has unfolded over about 13.8 billion years. That number is often called the age of the universe, but it must be understood carefully. It is the length of time from the very early hot and dense state that the current model can describe reliably to the present day. It does not automatically prove that absolutely nothing existed before that state, nor does it establish with certainty that time began precisely there. When scientists use present-day equations to trace the universe farther backward, matter becomes denser, temperatures become higher, and the structure of space grows increasingly extreme. Eventually, classical equations may lead to a state of infinite density, commonly called a singularity. But an infinite result in mathematics is not necessarily a real object that once existed in nature. It may instead be a sign that the theory has reached its limit. General relativity describes gravity and the structure of space with extraordinary precision on the scales of planets, stars, and galaxies. Quantum mechanics describes the world of the smallest particles. Throughout most of cosmic history, these two theoretical frameworks can be used under relatively separate conditions. But in the earliest state, where matter was both extremely small in scale and subject to immensely strong gravity, both become necessary. Humanity still does not have a complete theory that unites them. Science can therefore describe the very early universe, but it cannot yet state with certainty what happened at the deepest boundary of the past. There may have been a true beginning. A different state may have existed before the period of expansion. Or perhaps the very idea of before loses its familiar meaning when time itself did not yet have the structure it has today. This is the important difference between two statements that are often treated as though they mean the same thing. The first says that the universe was once hot and dense, then expanded and cooled. This is supported by several independent lines of observational evidence. The second says that all of reality emerged from nothing at one absolute moment. That is a deeper claim, and the Big Bang model alone is not enough to prove it. So even if scientists one day discover that the Big Bang was not the first chapter, the hot and dense history of the universe could remain intact. It might instead become a transitional stage, an opening that followed a period of contraction, or a boundary whose other side still lies beyond our present ability to observe. What would change is not what happened after the Big Bang. Atoms would still have formed, the first stars would still have ignited, and galaxies would still have grown within the darkness. Only the position of that stage within a potentially much longer history would change. But if humanity cannot look directly into the first moment, how do we know that the universe was ever truly hot and dense? The answer does not lie in a photograph of the original explosion. It lies in an extremely faint layer of light passing through every room, every planet, and every empty region between galaxies. It is light that left the universe before the first stars had appeared, and even today, it continues to quietly cover the entire sky. Everywhere around us, there is an extremely faint layer of light that the human eye cannot see. It travels through the space between planets, crosses the vast empty regions between galaxies, and is present even in the quiet room where we are sitting. This light does not come from the sun, nor does it originate from any particular star or galaxy. It arrives from nearly every direction in the sky, carrying traces of a distant era when the universe did not yet contain a single star. This is the cosmic microwave background, the oldest light humanity can observe directly. To understand why this light exists, we need to return to a very early period, when space was not transparent as it is today. At present, light from distant stars can travel for millions or billions of light years before reaching a telescope. For most of that journey, it moves through regions that are nearly empty and is only occasionally redirected by dust, gas, or another object. The early universe was entirely different. Matter had not yet been organized into stars, planets, or galaxies, but existed within a hot, dense, and nearly uniform environment filled with radiation and constantly moving particles. The temperature was so high that electrons could not remain bound to atomic nuclei for long. Whenever an electron approached a nucleus, the energy in the surrounding environment could quickly separate them again. Instead of the neutral atoms of hydrogen and helium familiar to us today, space contained a mixture of positively charged nuclei, negatively charged electrons, and countless photons. Photons are the quantum particles of light. In a vacuum, they can travel freely at the speed of light, but the early universe was not a quiet vacuum. Free electrons were present everywhere, so each photon could travel only a short distance before colliding with one and being redirected. The light did not disappear in those collisions. It remained present in enormous quantities, but it could not travel in a straight line across any great distance. Each photon was continually pushed in a new direction, like someone trying to cross a crowded room while constantly being diverted by the people moving around them. The universe at that time can be imagined as a room filled with thick fog. Light existed everywhere, but visibility extended only a short distance. The fog of the early universe was not made of water droplets, but of free charged particles distributed throughout all of space. During this period, there was no dark sky filled with separate points of light as we know it today. Light and matter were blended together within a hot, bright, and opaque environment. If it had somehow been possible to stand there, although such a thing could never truly happen, we would not have seen any distant object. Every direction would have been covered by the same dense glow, where light collided continuously with matter and could barely carry an intact image across any meaningful distance. All around us lies an extremely faint layer of light that the human eye cannot see. It travels through the space between planets, crosses the vast empty regions between galaxies, and is present even in the quiet room where we are sitting. This light does not come from the sun, nor does it originate from any particular star or galaxy. It arrives from nearly every direction in the sky, carrying traces of a distant era when the universe did not yet contain a single star. This is the cosmic microwave background, the oldest light humanity can observe directly. To understand why this light exists, we must return to a very early period, when space was not transparent as it is today. At present, light from distant stars can travel for millions or billions of light years before reaching a telescope. For most of that journey, it moves through regions that are nearly empty and is only occasionally redirected by dust, gas, or another object. The early universe was entirely different. Matter had not yet been organized into stars, planets, or galaxies, but existed within a hot, dense, and nearly uniform environment filled with radiation and particles in constant motion. The temperature was so high that electrons could not remain bound to atomic nuclei for long. Whenever an electron approached a nucleus, the energy in the surrounding environment could quickly separate them again. Instead of the neutral atoms of hydrogen and helium familiar to us today, space contained a mixture of positively charged nuclei, negatively charged electrons, and countless photons. Photons are the quantum particles of light. In a vacuum, they can travel freely at the speed of light, but the early universe was not a quiet vacuum. Free electrons were present everywhere, so each photon could travel only a short distance before colliding and being redirected. The light did not disappear during those collisions. It remained present in enormous quantities, but it could not travel in a straight line across any great distance. Each photon was constantly pushed in a new direction, like someone trying to cross a crowded room while repeatedly being diverted by the people moving around them. The universe at that time can be imagined as a room filled with thick fog. Light existed everywhere, but visibility extended only a short distance. The fog of the early universe was not made of water droplets, but of free charged particles spread throughout all of space. During this period, there was no dark sky filled with separate points of light as we know it today. Light and matter were blended together within a hot, bright, and opaque environment. If it had somehow been possible to stand there, although such a thing could never truly happen, we would not have seen any distant object. Every direction would have been covered by the same dense glow, where light collided continuously with matter and could barely preserve an intact image across any meaningful distance. The universe continued to expand. As space grew larger, the density of matter decreased and the temperature gradually fell. This process was extremely slow compared with a human lifetime, but on cosmic timescales, it steadily carried the original hot environment toward a new state. After about 380,000 years, the temperature had fallen to nearly 3,000 Kelvin. That was still extremely hot compared with familiar environments on Earth, but it was cool enough for electrons to begin attaching to nuclei and remaining bound for longer periods. Hydrogen nuclei captured electrons and formed neutral hydrogen atoms, while helium underwent a similar process. As the number of free electrons dropped sharply, photons no longer encountered so many charged particles along their paths. The fog gradually cleared, not in a single instant, but over a period during which more and more electrons became bound within atoms. Compared with a history lasting billions of years, however, this transition still occurred relatively quickly. Scientists call the process in which electrons attach to nuclei recombination. The name may suggest that they had previously combined and then separated. But in the thermal history of the universe, this was effectively the first time neutral atoms could form in large, stable numbers. The moment when photons were no longer trapped within the hot plasma is also regarded as the point when matter and radiation began to decouple, allowing light to begin a separate journey that would continue throughout the rest of cosmic history. The light observed today by radio telescopes consists of the photons that escaped from that first fog. They did not emerge from one special location, because all observable space once contained the same hot environment. This is why the ancient radiation appears in every direction. Wherever a telescope points in the sky, it can detect a tiny part of this background glow. That does not mean these photons remained motionless around us for billions of years. They have been traveling continuously. The photons reaching Earth today began their journey from a region of matter far away in the ancient universe, while the photons that left the region around what would one day become Earth traveled elsewhere long ago. The background radiation we observe forms a shell around the observer, often called the surface of last scattering. It is not a physical wall at the edge of the universe, but simply the farthest boundary from which light can carry direct information to us from that early period. Beyond that surface, the universe still existed, but because light was repeatedly scattered within the plasma, we cannot use photons to look farther back in the ordinary way. It is similar to standing before a thick cloud. The eye sees only the surface from which light last escapes, not through the entire cloud. The cosmic microwave background is therefore not an image of the moment the Big Bang occurred, and it does not reveal an absolute beginning. It shows the universe when it was about 380,000 years old, still an extraordinarily early stage compared with its present age of roughly 13.8 billion years, but not the first moment of history. Throughout the journey that followed, space continued to expand and stretched the wavelengths of those photons. When first released, the radiation had a color similar to the light from an object heated to around 3,000 Kelvin. If human eyes could somehow have existed under those conditions, the entire sky would have glowed with a warm, orange-red light. But over billions of years, as cosmic distances grew by more than 1,000-fold, the wavelengths of the photons were stretched by the same factor. Light that once lay within the visible range gradually shifted into the infrared and then continued into the microwave region. The energy of this light decreased with the expansion, and its characteristic temperature fell as well. Today, the cosmic microwave background has an average temperature of about 2.7 Kelvin, only slightly above absolute zero. It is far too cold for the body to feel and so weak that, in everyday life, it is completely overwhelmed by light from nearer objects. Yet despite being extremely cold, this radiation is not rare. Every cubic centimeter of space contains hundreds of cosmic microwave background photons present in the room around us, within the human body, and throughout the enormous empty regions between planets. Most of these photons simply pass through matter without leaving any trace we can perceive. But with instruments sensitive enough, humanity can measure their presence and reconstruct an image of the sky from before any stars had formed. The discovery of this radiation did not begin with a complete picture, but with a strange background noise that seemed impossible to explain. By the middle of the 20th century, scientists had predicted that if the universe had once been hot and dense, radiation left over from that era should still exist, even though expansion would have cooled it dramatically. In 1964, two radio engineers, Arno Penzias and Robert Wilson, were using a large antenna in the United States to study microwave signals. During their work, they repeatedly detected a background noise that appeared no matter where the antenna was pointed. The signal did not disappear at different times of day and could not be linked to any specific radio source in the sky. They checked the equipment, the cables, and the surrounding environment, even cleaning away material left by birds inside the antenna, but the noise remained. Eventually, the mysterious signal was recognized as radiation left over from the early universe. The discovery became one of the most important pieces of evidence supporting the hot Big Bang model, because a universe that had always existed in a state similar to the present would have great difficulty producing such a uniform layer of radiation from every direction with the correct temperature. Later, dedicated satellites measured the cosmic microwave background with increasing precision. What impressed scientists was not only its temperature, but also the shape of its energy spectrum. The radiation matches almost perfectly the spectrum of a black body, the type of radiation produced when light and matter have been in extremely close thermal equilibrium. Very few things in nature display such a nearly perfect black body spectrum. Even stars are not ideal, because their atmospheres absorb and emit light at many different wavelengths. The cosmic microwave background, however, preserves an almost perfectly pure thermal curve. This shows that the light was once trapped within a hot, dense environment long enough to reach equilibrium before being released when the universe became transparent. This is why the radiation carries such extraordinary weight. It does not merely reveal that microwaves fill the sky. Its temperature, uniformity, and energy spectrum all tell the same consistent story. The universe was once hotter and denser, with matter and radiation constantly interacting. Any theory that seeks to replace the current Big Bang model must explain this radiation. A universe that once contracted and then bounced must still produce a hot phase capable of creating plasma. A cyclic model must explain how the background radiation of the present cycle arose. A theory in which time began in some other way must still lead to a background with the correct temperature and structure. The story before that era may change, and the hot phase may not have been the absolute beginning, but the cosmic microwave background cannot simply be ignored because it is a directly measured part of the universe. Even more remarkable is that this ancient light is not perfectly uniform. With rough measurements, its temperature appears almost identical in every direction. But once instruments became sensitive enough, extremely small differences emerged. Some regions are slightly warmer and others slightly cooler, with variations of only about 1 part in 100,000. These differences are far too small to be felt, but they are not meaningless noise. Within those tiny temperature ripples lie traces of regions that were slightly denser or slightly less dense in the early universe. Over time, gravity amplified these almost insignificant differences. Matter gradually gathered into the denser regions, forming clouds of gas, the first stars, galaxies, and eventually the enormous cosmic web we see today. The cosmic microwave background is therefore more than light left over from an age without stars. It is also the earliest record of the seeds from which all later structure grew. Within that nearly featureless glow, the first galaxies did not yet exist, but the faint outline of the future had already begun to appear. When scientists look at the cosmic microwave background, they do not see only a layer of cold light spread almost uniformly across the sky. Hidden within that apparent smoothness are extremely small differences, regions that are slightly warmer or slightly cooler than their surroundings, with variations of only about 1 part in 100,000. If the average temperature of this ancient light were a calm lake, these differences would be like the faintest ripples across its surface, so subtle that they would be almost impossible to detect without instruments sensitive enough to measure them. These ripples are not random, nor are they merely noise produced by the detectors. They reflect the distribution of matter in the early universe at the time when space had just become transparent and light began traveling freely. A slightly warmer region may be associated with an area where matter was a little denser, while a slightly cooler region may represent a place where it was more thinly spread. The differences were extraordinarily small, yet it was from these faint variations that all the large-scale structure of the later universe gradually formed. The early universe was not a perfectly smooth mass of matter. If every region had exactly the same density, with nowhere even slightly thicker or thinner than anywhere else, gravity would have had no reason to draw matter toward any particular location. Gas would have remained evenly distributed through space, making it difficult for clouds dense enough to form stars to develop. Galaxies, galaxy clusters, and even the planets that came later might never have appeared. The tiny imperfections in the young universe were therefore not errors to be removed, but necessary conditions for a structured world to exist. The deeper origin of these early differences remains one of the major questions in cosmology. Many models suggest that they began as extremely small fluctuations within the physical fields of the very early universe and were later stretched to much larger scales. But to understand how galaxies formed, it is not necessary to go deeply into that still unobservable period. What matters is that by the time the cosmic microwave background was released, regions of slightly different density already existed. They were like faint marks of ink placed on a sheet of paper before the larger picture began to be drawn. From that point on, gravity continued its work for billions of years. A region containing even slightly more matter than its surroundings produced a somewhat stronger gravitational pull. It drew additional matter toward itself from nearby areas. As more material gathered, its gravity increased, allowing it to attract still more gas and dark matter. The process was slow, but it never stopped. A difference that was almost insignificant gradually became a clearly denser region, then a large concentration of matter capable of continuing to collapse. We can imagine a very shallow depression in a wide field. At first, the difference in height is almost impossible to notice. But once water begins to flow, a small amount collects there. That water encourages more flow from the surrounding area toward the same place, and the depression becomes increasingly distinct. Gravity in the universe works in a similar way, except that instead of drawing in water, it pulls gas, dark matter, and every form of matter with mass toward regions that are slightly denser. Throughout much of this process, dark matter played an important role. It does not emit light, reflect light, or reveal exactly what kind of particle it is. Yet its gravitational influence is clearly visible in the motions of galaxies, within galaxy clusters, and in the way light bends as it passes through regions containing large amounts of mass. In the early universe, dark matter may have begun gathering before ordinary gas did, creating gravitational regions that acted like invisible frameworks into which luminous matter would later fall. The original hydrogen and helium gas was more strongly affected by radiation than dark matter was. Before the universe became transparent, the pressure of light continually prevented the gas from collapsing too quickly. But after neutral atoms formed and photons began traveling freely, the gas was gradually released from that restraint. It began falling into already existing gravitational wells where the density of dark matter was greater than in the surrounding regions. For tens of millions of years after the cosmic microwave background was released, the universe contained no stars. Space had become transparent, but it was still dark because no new sources of light had yet formed. This period is commonly called the Cosmic Dark Ages. The name may sound mysterious, but it simply describes a time when the ancient background light had shifted to longer wavelengths and weakened, while the first stars had not yet had enough time to appear. Within that darkness, gas continued moving under the influence of gravity. Large clouds gradually became denser. As gas fell into a concentrated region, it did not simply travel straight toward the center. It collided, heated up, and moved through complex flows. Some of its energy had to be released for the cloud to continue collapsing. If cooling was efficient enough, the density near the center increased, creating the conditions for smaller clumps of gas to form within it. Eventually, some regions became dense and hot enough for nuclear reactions to begin. Hydrogen in their cores was converted into helium, releasing energy. The first stars ignited. They were not entirely like most of the stars familiar to us today. Because the universe at that time contained almost no heavy elements, the first stars were made primarily of hydrogen and helium. Many models suggest that they may have been extremely massive, hot, and luminous, but relatively short-lived. Within their cores, heavier elements began to form. When some of these stars ended their lives in powerful explosions, material enriched with carbon, oxygen, and many other elements was released back into space. Later generations of stars were born from gas that was no longer completely pristine. Each cycle of stellar birth and death continued to alter the chemical composition of the surrounding environment. Over time, the elements needed for rocky planets, oceans, and life gradually appeared. But during this early stage, the entire process was still unfolding within regions of matter that had grown from the tiny density ripples of the young universe. The first stars did not exist in isolation within completely empty space. They formed inside concentrations of matter held together by gravity. Smaller structures could merge, carrying gas, stars, and dark matter with them. Through repeated collisions and mergers, larger systems gradually emerged. This was one of the paths that led to the formation of the first galaxies. A galaxy is not a random collection of stars standing near one another. It is a gravitationally bound system made of stars, gas, dust, stellar remnants, black holes, and a large amount of dark matter. The luminous portion visible through telescopes is only one part of the full structure. Surrounding many galaxies is a much larger region of dark matter that forms the gravitational framework holding everything together. Early young galaxies were often far smaller than many of the large galaxies we see today. They did not immediately appear as stable spirals or broad halos of stars. They grew gradually by drawing in more gas, forming new stars, and merging with smaller systems. Some mergers distorted the shapes of galaxies, compressed their gas, and triggered intense bursts of star formation. Others unfolded more slowly, quietly adding material over hundreds of millions of years. Even the Milky Way is believed to have matured in this way. Our galaxy did not form fully assembled in a single moment, but was built through many stages. The oldest stars in its halo may preserve traces of smaller systems that were once absorbed by the Milky Way. In the surrounding space, long streams of stars can still be observed as remnants of small galaxies torn apart by gravity. Growth did not stop at the level of individual galaxies. Galaxies also attracted one another. Nearby systems could form groups in which several large galaxies and many smaller ones moved around a shared gravitational center. The Milky Way belongs to such a group, together with the Andromeda Galaxy and dozens of smaller members. On larger scales, groups can gather into galaxy clusters containing hundreds or thousands of galaxies. Between them lies extremely hot gas that emits X-rays, along with enormous amounts of dark matter. A galaxy cluster is not merely a crowd of galaxies that happen to appear close together in the sky. It is a vast gravitational structure whose members move within a shared gravitational field. Yet even galaxy clusters are not distributed evenly throughout space. As maps of the universe expanded, a still larger pattern began to emerge. Galaxies and galaxy clusters often lie along extended filaments that intersect at dense regions. Between those filaments are enormous, empty areas where the number of galaxies is much lower. This structure is known as the cosmic web. Viewed on a large enough scale, it can resemble a spider web, a network of tree roots, or waterways stretching across a vast landscape. The filaments are not simple straight lines, but complex regions where gas, galaxies, and dark matter gather together under gravity. Between the filaments lie voids of immense size. They are not completely empty, but they contain far less matter than the surrounding regions. As structure developed, matter was gradually drawn out of the less dense areas and flowed toward the filaments and their crowded intersections. The voids, therefore, became increasingly empty, while denser regions grew more pronounced. This growth resembles small drops of water gathering into streams. At first, there are only slight differences across a surface that is almost level. Water gradually moves toward lower channels, smaller grooves join together, and eventually they form creeks, rivers, and an entire network flowing across the land. In the universe, gravity provides the guidance, while matter moves according to density patterns that were established very early. The image of flowing water, however, is only a visual analogy. Matter in the universe does not move across a fixed surface, nor is there a single downward direction. Each dense region creates its own gravitational field, drawing matter inward from many directions through three-dimensional space. The result is a network with no common center, extending across hundreds of millions of light years. What is especially important is that the present shape of the cosmic web is not separate from the ripples seen in the cosmic microwave background. When scientists measure the distribution of millions of galaxies and compare it with maps of the ancient light, they find that the two pictures can be connected through the same process of gravitational growth. Slightly denser regions in the young universe became favorable places for structure to form, while less dense regions gradually developed into voids. It is impossible to track every individual particle of matter directly across 13.8 billion years, but computer simulations can begin with a universe containing density ripples, similar to those seen in the cosmic microwave background, and then allow gravity to act over time. When the properties of ordinary matter, dark matter, and cosmic expansion are included appropriately, these simulations produce networks with many of the same features observed through telescopes. At first, the model contains only very small differences. Over time, dense regions collapse, sparse regions become emptier, filaments emerge, and their intersections grow. Within these concentrated regions, galaxies form and continue to merge. The result does not reproduce every individual real galaxy exactly, because the history of each region includes many random factors, but the overall structure closely resembles the observable universe. This is one of the major successes of the modern Big Bang model. It does not merely explain that the universe was once hotter. It also connects an early state that was almost uniform with the present universe, which contains countless complex structures. The ripples in the cosmic microwave background did not remain only as ancient traces. They became the starting point for the formation of galaxies, galaxy clusters, and the vast web surrounding us today. Even so, Many details of this process are still not completely understood. The exact nature of dark matter remains unknown. The ways gas falls into galaxies, forms stars, and is then driven back outward by explosions and black holes are extremely complex. The earliest galaxies may have grown faster than some simple models once predicted. Scientists therefore continue refining the way they describe the formation of cosmic structure. These uncertainties do not erase the fundamental connection between the early ripples and the universe we see today. They show that even within a broadly successful picture, many details still need to be filled in. A model may explain why structure appeared while still requiring improvement to describe each stage of star formation, every type of galaxy, and the many different environments in which they developed. If the current Big Bang model must one day be expanded, this connection will remain a difficult test for any alternative. Every new theory must explain why the cosmic microwave background contains variations at exactly the observed level, and why, after billions of years, those variations developed into a network of galaxies resembling what appears in the deepest maps of space. A bouncing universe model may change the story before the hot phase, but it must still produce the right seeds. A cyclic universe may extend cosmic history farther into the past, but it must explain how the ripples of the present cycle formed. A new theory of gravity may change the rate at which structures grow, but it must agree at the same time with the cosmic microwave background, the distribution of galaxies, and the motions within galaxy clusters. The galaxies we see today are therefore more than bright objects scattered through darkness. They are the final results of a process that has unfolded across nearly the entire age of the universe. Their shapes, locations, and motions still preserve traces of tiny differences that existed before the first star ignited. The Milky Way, the Sun, Earth, and every atom within the human body all appeared within one small branch of that web. The region of space where we now exist was once part of the faint density fluctuations of the early universe. Through gravity, star formation, and many generations of recycled matter, a ripple that was almost impossible to detect gradually led to structures complex enough to look back and investigate their own origins. The ancient light shows that the universe was once hot and nearly uniform. The cosmic web shows that the small seeds within it truly grew. These two pictures, separated by billions of years, remain connected by one consistent story. But the cosmic microwave background is not the only trace of the early universe. Long before that light was released, when the universe had existed for only a few minutes, another process left marks that remain within almost every star and cloud of gas today. During that brief interval, the first atomic nuclei formed, establishing the material foundation for the entire history that followed. Long before the first stars began to shine, matter in the universe passed through a brief but decisive stage of transformation. There were no complete atoms yet, no cold clouds of gas, and no heavy elements capable of forming rocks, oceans, or life. All of space was still so hot that familiar structures of matter could not remain stable. Yet within that intense environment, the first components of atomic nuclei began to join together. The nucleus is the extremely small region at the center of an atom. Most of an atom's mass is concentrated there, while much lighter electrons move through the surrounding space. But in the early universe, electrons could not yet bind to nuclei and form complete atoms. The temperature was too high, causing them to move freely through a dense sea of radiation. The story of the first few minutes is therefore not the story of atoms forming, but of the simplest atomic nuclei beginning to appear. The two main components of a nucleus are protons and neutrons. Protons carry a positive electric charge, while neutrons carry no charge. The nucleus of an ordinary hydrogen atom contains only one proton. Helium is more complex, because its most common nucleus contains 2 protons and 2 neutrons. Structures this small may sound simple, but in an extremely hot universe, even keeping a few particles bound together was difficult. During the earliest moments, Protons and neutrons moved through an environment of immense density and temperature. They constantly collided with other particles and could also transform into one another through interactions taking place on extremely small scales. As the universe expanded, the temperature gradually fell and these conversion processes slowed. Protons then became more numerous than neutrons. This imbalance later determined why hydrogen makes up most ordinary matter, while helium accounts for a smaller portion. Even after the temperature had fallen, nuclei could not form immediately. The radiation filling the universe still contained countless high-energy photons. A photon is a particle that carries the energy of light. At this stage, many photons were energetic enough to break apart a nucleus almost as soon as it formed. Protons and neutrons could meet, bind together for a moment, and then be separated again by another collision. The first important step was the appearance of deuterium. This is a special form of hydrogen whose nucleus contains one proton and one neutron. Ordinary hydrogen contains only one proton, so deuterium is slightly heavier. This structure served as the first bridge toward the formation of larger nuclei, but for a time, that bridge was constantly destroyed by radiation. The universe continued to expand and cool. Gradually, the number of photons energetic enough to break deuterium apart declined. Small nuclei began surviving for longer periods, giving them enough time to encounter additional protons or neutrons and enter further reactions. A nuclear reaction is a process in which nuclei combine, split apart, or change their structure, producing a different kind of nucleus. In the early universe, this chain of reactions led from deuterium to lighter forms of helium, and finally to helium-4, the form of helium containing 2 protons and 2 neutrons. Helium-4 is extremely stable. Once neutrons became bound within this structure, they were no longer as likely to decay as they would have been in isolation. Most of the remaining neutrons were therefore quickly incorporated into helium. The protons that did not take part remained separate and later became the nuclei of hydrogen atoms. This entire stage lasted only through the first few minutes of cosmic history. The universe at that time can be imagined as a nuclear reactor extending everywhere, although this image must be understood carefully. There was no flame at the center and no cooler shell surrounding it. Every region of space participated in the creation of nuclei, because the whole observable universe was then in a hot, dense state. That vast reactor could not remain active for long. Continuous expansion reduced the density of matter, so particles encountered one another less and less often. The temperature also fell, preventing many reactions from occurring quickly enough. The right conditions opened for only a brief interval and then closed again. The universe did not have enough time to continue building progressively larger nuclei. The result was relatively simple. Most ordinary matter remained in the form of hydrogen. A smaller portion became helium. There were also tiny amounts of deuterium, a lighter form of helium, and a small quantity of lithium. Lithium has a nucleus larger than those of hydrogen and helium, but only a very small amount was produced in the early universe. Heavy elements such as carbon, oxygen, and iron had scarcely appeared. Carbon would later become the foundation of life, oxygen would help form water, and iron would be found in planetary cores and in human blood. But these elements require more stages of nuclear reactions and conditions that remain stable for much longer. The early universe cooled too quickly to complete that work. The task of producing heavy elements was passed on to the stars. Once stars formed, gravity kept gas compressed within their cores for millions or billions of years. High temperatures were maintained long enough for hydrogen to gradually become helium, and in older stars, helium later participated in the production of carbon and oxygen. Massive stars also built still heavier elements before reaching the ends of their lives. Through stellar explosions and other powerful processes, matter transformed within stellar cores was released back into space. Later generations of stars formed from clouds of gas enriched with more elements. After many cycles of formation and destruction, the universe gradually accumulated enough carbon, oxygen, silicon, iron, and other ingredients to create rocky planets. Even so, most hydrogen in the universe was not produced by stars. It has existed since the first few minutes. The nucleus of a hydrogen atom in a distant cloud of gas may have formed before any galaxy existed, drifted through space for billions of years, and only later fallen into a star or planetary system. Helium also carries an extremely ancient history. Some additional helium was created within stars, but a large amount was already present before the first source of light appeared. It is this ancient origin that makes hydrogen and helium such important witnesses. Astronomers cannot travel back to observe the first few minutes directly, but they can measure the composition of distant gas clouds that have been altered only slightly by generations of stars. Regions like these preserve a mixture closer to the original material than places that have undergone many cycles of star formation. Using known nuclear laws, scientists can calculate how much of each light element should have formed in a universe that was expanding and cooling. The result depends on the density of matter, the temperature, the expansion rate, and the ratio of protons to neutrons. When these predictions are compared with observations, the amounts of hydrogen and helium generally agree well with the picture of a hot Big Bang. Deuterium is especially valuable in this test. After it formed in the early universe, deuterium was easily destroyed inside stellar cores but was difficult to produce again in large quantities. Gas clouds that still contain relatively high amounts of deuterium are therefore often regarded as regions that have not been deeply altered by stellar activity. The amount of deuterium within them helps scientists estimate the conditions of the universe when the first nuclear reactions took place. Helium provides another trace. Regions with very few heavy elements still contain a significant amount of helium, even though they have not experienced enough generations of stars to produce all the helium that is observed. This indicates that most helium was already present before stars began to operate. When deuterium, hydrogen, and helium all point toward a similar picture, the evidence becomes far stronger than it would be if it depended on only one element. Even within this agreement, however, one unresolved issue remains involving lithium. The hot Big Bang model predicts a higher original abundance of lithium than is usually found in the atmospheres of some very old stars. These stars formed when the universe contained few heavy elements, so their composition may preserve traces of ancient material. The difference between prediction and observation is known as the lithium problem. This name does not mean that the entire process of primordial element formation is wrong. It simply shows that one part of the picture is not yet fully understood. Lithium may have been carried from the surfaces of stars into deeper layers, where it was destroyed. The movement of matter inside old stars may also be more complicated than present models describe. Rare nuclear reactions or some unknown feature of the early universe are also being considered. The lithium problem remains a serious question, but hydrogen, helium, and deuterium continue to agree reasonably well with the model. In science, one mismatch does not automatically invalidate an entire theory. Researchers must first determine whether the difference comes from the data, from the way stars are modeled, or from a missing piece of physics. Only when many independent measurements lead to a contradiction that cannot be resolved does the foundation of a model truly come under severe pressure. The light elements therefore carry two meanings at once. They strongly support the idea that the universe was once hot and dense, while also reminding us that the present picture is not complete in every detail. Science does not need to hide what remains unclear. Small discrepancies are often what open the path toward deeper understanding. The cosmic microwave background records the time when the universe became transparent. The small ripples within that light show that the seeds of galaxies already existed. Hydrogen, helium, and deuterium carry the story farther back, to the first few minutes when there were still no atoms or stars. These three traces come from very different periods, yet all point toward a past that was hotter and denser than the universe today. This consistency is why the hot Big Bang model remains strong. A new theory may change the way humanity understands what happened before the hot phase, but it cannot ignore the elemental composition observed throughout the universe. Cosmic history may be extended beyond the Big Bang, yet the stage that produced hydrogen and helium must still appear somewhere within the new model. A universe that contracted before expanding would still need to pass through a state hot enough for nuclear reactions to occur. A history made of repeated cycles would still have to explain why the present cycle began with the observed mixture of light elements. Even a model without a clearly defined moment of creation would still need to produce a brief interval during which protons and neutrons could combine. For this reason, the question of whether the Big Bang was the absolute beginning is different from the question of whether the universe ever passed through a hot, dense phase. The traces of that hot phase are clearly present in ancient light and in chemical composition. What remains open lies deeper, at the point where current theories can no longer describe with confidence what may have existed before. During the first few minutes, the universe produced only a simple set of ingredients. Hydrogen and helium drifted through the starless ages, then gradually gathered under gravity. From those clouds, the first sources of light formed and continued the work that the early universe had left unfinished. Over billions of years, these simple nuclei became stellar fuel and indirectly opened the way for more complex elements to appear. The universe's first nuclear reactor operated only briefly, but its products remain everywhere. The hydrogen burning in the core of the sun, the helium found within stars, and the deuterium still preserved in distant gas clouds all carry the material memory of that era. They do not reveal with certainty what happened before the hot Big Bang, but they confirm that a phase of extremely high temperature truly existed. The major lines of evidence have now come together. The universe was once hot. Light was once trapped within opaque matter. Light elements formed during the first few minutes, and tiny density ripples later grew into galaxies. That foundation remains relatively secure. The questions now causing cosmologists to reconsider parts of the story lie elsewhere. Measurements of the expansion rate do not yet agree perfectly. Some galaxies appear to have formed surprisingly early, and the component driving the expansion of space remains almost entirely unexplained. The Big Bang has therefore not disappeared. What is gradually becoming clearer is the possibility that the familiar story is still missing several pages, especially in the part that comes before the hot phase and in the details that govern how the universe developed afterward. After decades of observation, the picture of cosmic history has become much clearer. Ancient light shows that space was once hot and opaque. The light elements preserve traces of reactions that took place during the first few minutes. The galaxies we see today reveal how tiny ripples in matter grew under the influence of gravity. Each part of the story seems to follow naturally from the one before it, from an almost uniform universe to the vast cosmic web now surrounding us. Yet a picture can be correct in its broad outlines, while still containing details that do not fit perfectly. As instruments become more sensitive, uncertainties shrink, and the number of observed objects increases, differences that were once hidden begin to stand out. They do not cause the entire story to collapse at once. Instead, they are like two extremely precise clocks running in the same quiet room, only to show slightly different times after many years. The gap may be small, but the very precision of the clocks means it cannot be ignored. The most widely discussed difference concerns the rate at which the universe is expanding. This number describes how quickly the distance between very remote galaxies is increasing at the present time. Astronomers call it the Hubble constant, named after the scientist who helped show that distant galaxies generally recede from us faster than nearby ones. The word constant does not mean the expansion rate has remained unchanged throughout cosmic history. It refers only to the value used to describe expansion in the present era. This number cannot be measured by placing a ruler between two galaxies. The distances are far too large, and the light from remote objects has traveled through space for millions or billions of years. Astronomers therefore build a chain of measurements in which each step helps establish the next. This method is commonly called the cosmic distance ladder because it resembles a ladder leading gradually from relatively nearby stars to galaxies much deeper in space. The first step relies on stars whose distances can be determined geometrically. Farther away, astronomers use a type of star whose brightness changes in a steady rhythm. These are called Cepheid variable stars. The length of each cycle of brightening and dimming is related to the amount of light the star truly emits. Once the intrinsic brightness is known and compared with how bright the star appears from Earth, its distance can be estimated. From galaxies containing Cepheid stars, the latter extends to a special kind of stellar explosion known as a Type Ia supernova. A supernova is a stage in which a star or stellar remnant releases an enormous amount of energy and becomes intensely bright for a short period. Type Ia supernovae have relatively similar true brightness after correction, allowing them to measure distances far beyond the reach of Cepheid stars. By combining these steps, astronomers obtain a present-day expansion rate close to 73 kilometers per second per megaparsec. A megaparsec is a unit of distance commonly used in astronomy and is equal to about 3.26 million light-years. The meaning of this number is not especially complicated. For every additional megaparsec of distance, the average recession speed caused by cosmic expansion increases by about 73 kilometers per second. At relatively nearby distances, the individual motion of each galaxy can make the measurements more complicated. But when astronomers observe on sufficiently large scales, the overall trend becomes clear. The greater the distance, the higher the average recession speed. This is not because Earth occupies a special central location, but because the space between galaxies is expanding. A different path leads to a lower value. Instead of beginning with nearby stars in the present universe, this method looks back to the cosmic microwave background, the light released when the universe was about 380,000 years old. The small ripples within that background depend on the composition and condition of the young universe. Scientists then place those measurements into the Standard Model and calculate how the universe should have evolved over the billions of years that followed. The Standard Model describes the universe using ordinary matter, dark matter, and dark energy. Ordinary matter forms atoms, stars, and planets. Dark matter emits no light but produces gravity, helping galaxies and large-scale structure form. Dark energy is the name given to the still unknown cause behind the accelerating expansion of space. When these three components are combined with cosmic microwave background data, the present expansion rate is inferred to be close to 67 kilometers per second per megaparsec. The difference between 67 and 73 may not seem large in everyday human terms, but these values do not come from rough estimates. They are based on years of observation, many instruments, and methods that have been tested repeatedly. As uncertainties continue to shrink while the two results still fail to converge, the difference begins to carry deeper significance. This problem is known as the Hubble tension. The word tension does not mean that one side is certainly correct and the other is certainly wrong. It simply means that two reliable approaches are producing results that are difficult to place within the same model. The source may lie in an undiscovered measurement error, in the way stars are modeled, or in the history of expansion assumed by the current theory. One suspicion once focused on images taken by the Hubble Space Telescope. In distant galaxies, many stars are packed so closely together that their light can overlap within a single pixel, making Cepheid stars appear brighter than they really are. An incorrect brightness would lead to an incorrect distance and then affect the expansion rate calculated at the top of the ladder. The James Webb Space Telescope can observe with greater sharpness at infrared wavelengths, where light from many distant stars can be separated more clearly. Wavelength is the distance between two successive peaks of a light wave, and infrared light has longer wavelengths than the red light visible to the human eye. When Webb re-examined many Cepheid stars previously observed by Hubble, the two telescopes produced consistent results. One important possible source of error was therefore reduced, yet the gap between the two expansion rates remained. This does not immediately prove that new physics lies behind the difference. The distance ladder contains many steps, and every step includes details that must be checked. The cosmic microwave background data also does not produce the number 67 by itself. That result depends on using the Standard Model to connect the young universe with the present. If the history between those two times contains an unknown component, the inferred value could change. The Hubble tension, therefore, does not directly deny that the universe was once hot. The cosmic microwave background still exists and still carries a thermal spectrum consistent with a hot, dense phase. The question concerns what happened afterward. The universe may have expanded at a slightly different pace than the present model assumes, or a form of energy may have appeared during an early period and then faded, changing the way the cosmic microwave background should be interpreted. While research teams continue checking these two cosmic clocks, another telescope has revealed a different surprise from the era when the first galaxies were beginning to form. James Webb was designed to collect infrared light from extremely distant objects. Because space expanded while that light traveled, its wavelengths were stretched and shifted toward the red end of the spectrum. This phenomenon is called redshift. A greater redshift usually means the light left its source at an earlier time in cosmic history. Webb's first observations suggested that the young universe was brighter and more active than many researchers had expected. Some galaxies appeared only a few 100 million years after the hot Big Bang, yet already contained enough stars to shine clearly. Some systems showed relatively developed structures, while large black holes were also found at earlier times than anticipated. A black hole is a region of space where gravity is so strong that light crossing a certain boundary cannot escape. When gas falls toward a black hole, it does not immediately disappear. It often spirals around the outside, becoming compressed and heated until it emits enormous amounts of light. A young galaxy containing a black hole that is actively consuming matter can therefore appear far brighter than its true population of stars alone would suggest. This detail helped soften some of the earliest surprises. In the first images, a galaxy's brightness was often used to estimate its stellar mass. When part of that light actually came from hot gas around a black hole, the galaxy's mass may have been overestimated. Later, spectroscopic measurements also showed that some objects were not as distant or as massive as initially believed. Spectroscopy is the process of separating light into many wavelengths, similar to the way a prism divides white light into a band of colors. Every element and every physical environment leaves characteristic lines within that spectrum. Through spectroscopy, astronomers can determine distance, gas composition, star-forming activity, and signs of black holes more reliably than they can by examining color alone in an image. When people hear the claim that the Big Bang theory is collapsing, it is easy to imagine the entire history of the universe suddenly losing its foundation. Ancient radiation would no longer have meaning. The age of the universe would become inaccurate. Galaxies would lose any clear origin, and everything ever said about the earliest eras would have to begin again from nothing. But science rarely changes in such a sudden way. A major model is usually made of many parts with different levels of certainty, much like a house composed of a foundation, a supporting frame, separate rooms, and a roof. One room needing repairs does not mean the entire structure has lost its value, and replacing the roof does not necessarily remove the foundation beneath it. The Big Bang is also not a single idea supported by a single piece of evidence. In ordinary conversation, the name often gathers several different layers into the same story, from the hot state of the early universe to the deeper question of the first moment itself. These layers are connected, but they are not identical. Some have been observed through several independent lines of evidence, some are inferred through models, and others remain close to the boundary where present-day physics cannot yet provide a confident answer. The layer closest to direct observation is the idea that the universe was once hotter and denser than it is today. This is commonly called the hot Big Bang model. The name does not describe a fireball exploding into darkness. It refers to an era when all observable space contained matter and radiation at extremely high temperatures. The universe then expanded, became less dense, and gradually cooled, allowing nuclei, atoms, stars, and finally galaxies to appear in sequence. This part of the model is supported by the traces we have already followed. Hydrogen and helium show that nuclear reactions occurred when the universe was only a few minutes old. The cosmic microwave background preserves an image of the time when space became transparent. The extremely small ripples within that ancient light could develop into the cosmic web of galaxies observed today. These 3 lines of evidence come from 3 different periods, yet all point toward a history that was hot, dense, and expanding. A disagreement over the present expansion rate is therefore not enough to erase the hot Big Bang. A galaxy appearing earlier than predicted does not cause the cosmic microwave background to disappear. Whether dark energy changes over time remains an important question, but the answer does not necessarily affect the fact that hydrogen and helium formed during the first few minutes. Modern problems may force humanity to revise the detailed description while preserving the early hot history beneath it. Above that foundation lies the layer of the model used to explain the universe from its early stages to the present day. It must answer many questions at once. Why galaxies formed at the observed rate, what keeps them bound together, why expansion is accelerating, and how the components of matter are distributed through space. To accomplish this, the current model uses 3 main components. The first component is ordinary matter, meaning everything made of atoms. Stars, planets, intergalactic gas, cosmic dust, and the human body all belong to this category. Although ordinary matter forms nearly every luminous object visible through telescopes, it accounts for only a small part of the universe's total composition. Most of the mass required to explain the motions of galaxies appears to belong to a component that emits no light. This component is called dark matter. The word dark does not mean that it is black in color. It simply indicates that it does not absorb, reflect, or emit light in ways that ordinary telescopes can easily detect. Its existence is inferred from gravity. Stars in the outer regions of many galaxies move faster than the visible matter alone should be able to hold them. Galaxy clusters also contain more gravitational influence than can be explained by the combined mass of their observable stars and gas. Light from distant objects is also bent as it passes through regions containing large amounts of mass, allowing astronomers to map invisible material distributed around galaxies and galaxy clusters. These observations indicate an additional source of gravity, even though its true nature remains unknown. In the current model, dark matter is generally treated as a form of matter that moved relatively slowly during the era when cosmic structures began to form. This property allowed it to gather under gravity, creating invisible concentrations into which ordinary gas later fell. Galaxies could therefore grow within gravitational frameworks that had already begun to develop. But dark matter may be more complicated than this simple picture suggests. It may consist of several kinds of particles, interact very weakly with itself, or possess properties not included in the basic model. A change in the nature of dark matter could affect how quickly the first galaxies formed, the shapes of small galaxies, and the way matter is distributed within clusters. In that case, what would need revision is the description of the invisible component, not the evidence that the universe was once hot. The third component is called dark energy. This is the name given to the unknown cause behind the accelerating expansion of the universe. Throughout most of early cosmic history, the gravity of matter gradually slowed the expansion. But as the universe became more diffuse, another effect began to dominate, causing the distances between gravitationally unbound galaxies to increase at an ever faster rate. The term dark energy can create the impression that scientists already know it to be a specific form of energy. In reality, it is mainly a label for an observed phenomenon. The simplest explanation proposes that space itself contains an almost constant energy density. As space expands, the total amount of energy associated with it increases, and the influence of this component gradually overtakes the gravitational attraction of matter across large scales. Another possibility is that dark energy is not entirely constant. It may change very slowly over time, arise from an unknown physical field, or simply indicate that our current theory of gravity does not fully describe the universe across the greatest distances. A physical field is a quantity that exists throughout space and can carry energy. much like the electromagnetic field surrounding an electric charge or a magnet. A new field that changes over time could cause cosmic expansion to develop differently from the simplest prediction. Changing our understanding of dark energy would partially rewrite the history of cosmic expansion and the future of the universe. The rate at which galaxies move apart could be different. The inferred ages of certain eras might shift slightly, and the long-term fate of space would change as well. Yet a changing form of dark energy could still exist within a universe that once passed through a hot, dense state. The upper level of the house would be renovated while the foundation remained in place. A deeper revision could emerge within the theory of gravity itself. Gravity is currently described with great success by general relativity, in which matter and energy curve space and time, while objects move according to that curvature. The theory explains planetary orbits, the bending of light, black holes, gravitational waves, and many other phenomena with remarkable precision. Even so, most direct tests have taken place within the solar system, around stars and black holes, or across distances far smaller than the scale of the entire universe. Over billions of light years, gravity may produce extremely subtle effects that have never been recognized in nearby environments. An expanded version of the theory might explain cosmic acceleration without requiring dark energy in its present form, or it might change the rate at which large-scale structures grow. Models of this kind face a difficult challenge. They must not only explain the accelerating expansion, but also preserve every success of general relativity in the places where it has already been tested. A change that is too strong could produce incorrect planetary orbits or alter the way light bends. A new theory must therefore behave almost exactly like the old one under familiar conditions, revealing differences only on extremely large scales or within special environments. Dark matter, dark energy, and gravity together form the layer of the model that describes the mature universe. This is also where many of today's unresolved tensions are concentrated. The disagreement over the expansion rate may arise from an unknown energy component. The early appearance of galaxies may be connected to dark matter or to the process of star formation. Differences in how strongly matter is concentrated could suggest that structure developed somewhat differently from current predictions. All of these possibilities are important, but they do not directly reach the deeper layer of the hot Big Bang. Beneath the present description of the universe's components lies a proposed period intended to explain the unusual condition of the very early universe. This period is called cosmic inflation. The word inflation here has nothing to do with economics. It describes an extremely brief interval during which space is thought to have expanded at an extraordinary rate before the universe entered its hot state. The idea of inflation was proposed because the observable universe has several features that are difficult to explain through ordinary expansion alone. The cosmic microwave background has almost the same temperature in regions separated by enormous distances, even though, according to a simple calculation, those regions do not appear to have had enough time to exchange light and reach the same temperature. The geometry of space is also very close to flat on large scales. At the same time, the initial density variations have sizes and distributions suitable for producing galaxies. A period of extremely rapid expansion could connect these features. Before inflation, a small region may have been close enough together to reach an almost uniform state. Space then expanded dramatically, stretching that region until it became larger than the entire observable universe. Tiny fluctuations in the original environment were also stretched, becoming the seeds of later structure. When inflation ended, the energy driving the rapid expansion was converted into matter and radiation. The process that created this hot environment is commonly called reheating. The name refers to space becoming filled with high-energy particles after inflation, beginning the history of the hot Big Bang. This creates an important distinction. In many modern models, the hot Big Bang was not the first moment, but a phase that followed inflation. The hot, dense universe still existed, but it already had a history before that stage. Even within the familiar model, The Big Bang, therefore, does not necessarily mean that everything emerged from nothing. Inflation explains many broad features, but its exact mechanism remains unclear. No one knows precisely which physical field drove it, why the period began, how long it lasted, or exactly how it ended. There are many different models of inflation, each using a different form of energy and leaving slightly different predictions. Some have been ruled out by data, some remain consistent with observation, and some are extremely difficult to distinguish with present-day measurements. Inflation could therefore be revised or replaced without removing the hot phase that followed. Another model might produce uniformity, flatness, and the initial ripples through a process that did not require extremely rapid expansion. The universe may once have contracted and then transitioned into expansion. It may also have passed through a long-lasting state before entering the hot era. Each possibility must still produce the cosmic microwave background and the structures we observe, but the opening of the story would be different. Deeper than inflation lies the question of the singularity. A singularity is the name given to a boundary where present equations predict that density, temperature, or the curvature of space rises without limit. When cosmic expansion is traced backward using general relativity, distances continue to shrink and density continues to rise until the description approaches such a limit. The word point can be misleading because it encourages us to imagine a tiny speck of matter located somewhere within space. But the Big Bang singularity is not an object that can be placed at a coordinate. In the classical model, it appears at the past boundary of all space. Every observable region is traced backward toward that same extreme state. An infinite value in an equation does not necessarily mean that nature truly contains a place of infinite density. In many areas of physics, infinity often signals that a model is being used beyond the range in which it can operate. General relativity describes gravity on large scales extremely well, but it does not fully include the quantum effects that govern the smallest scales. Quantum physics is the theoretical framework used to describe particles and energy at extremely small scales. In that world, many quantities do not possess completely definite values before they are measured, and even empty space contains faint fluctuations. When the entire universe is compressed into an extremely small state and gravity becomes extraordinarily strong, both quantum physics and general relativity must be used together. Humanity does not yet have a complete theory of quantum gravity, meaning a single framework that combines gravity with quantum laws. Because of this gap, science cannot confidently describe the earliest boundary. The singularity may have existed in some physical sense, but it may also disappear once a deeper theory is introduced. In some models, quantum effects prevent space from contracting to zero size. The universe reaches an extremely high density and then transitions from contraction to expansion, producing a bounce. In other models, time near the earliest boundary no longer behaves like the time familiar to us, so there is no sharply defined moment that can be called the beginning. Other lines of research suggest that space and time may be phenomena emerging from a deeper structure, much as temperature has meaning only when a large number of particles exist together. This is the layer of the Big Bang story most open to change because it lies farthest from direct observation. Humanity can measure the cosmic microwave background, elemental abundances, and the distribution of galaxies, but cannot use light to look directly into the first few minutes, much less observe the state in which current laws lose their validity. The farther back we move into the past, the more the story depends on extending theories into conditions that have never been fully recreated. What is most likely to collapse first, therefore, is not the evidence for a hot phase, but the idea that the singularity in the equations represents the absolute beginning of all existence. Cosmic history may extend far beyond that boundary. The hot Big Bang would then become a transitional phase in which an earlier state transformed into the expanding universe. The image of a house helps make these layers clearer. The foundation consists of observations supporting a hot universe, the light elements, the cosmic microwave background, and expansion. Above it stands the framework describing dark matter, dark energy, and the growth of structure. The roof represents ideas about inflation and the earliest state, where the evidence is more indirect and the answers remain incomplete. A room in the house may need renovation if dark matter turns out to possess properties different from those predicted. The roof may be replaced if inflation gives way to a period of contraction. The foundation itself may also be extended through a deeper theory. But the new structure must still support everything that remains standing. It must explain hydrogen and helium, the 2.7 Kelvin background glow, the ripples in the cosmic microwave background, and the cosmic web of galaxies. A new theory cannot simply remove one difficult part while ignoring earlier successes. It must reproduce those successes in a more natural way while also explaining what does not yet fit. This is why science does not quickly abandon a model because of one surprising observation. A replacement model must accomplish more, not merely tell a different story. The history of science has passed through changes like this before. Newton's laws of motion still describe objects moving at low speeds and within gravitational fields that are not too strong with great accuracy. Einstein's theory of relativity did not make those laws meaningless. It placed them within a broader framework and revealed the limits at which they needed to be modified. A future theory of the universe may treat the Big Bang in much the same way. Within that new framework, the hot Big Bang could remain an accurate description of one era. What would change is how that era began, which components governed expansion, and what existed beyond the earliest boundary. The old story would not be erased completely, but placed within a much wider history. Modern cosmology, therefore, does not face a simple choice between the Big Bang being right or wrong. The real questions are far more subtle. Which parts have been directly observed? Which depend on a model? Which appear only when equations are pushed to their limits? Once these three questions are separated, claims about the collapse of the Big Bang become less dramatic, but they open the way to a deeper possibility. The universe was once hot and dense, and that will almost certainly remain part of its history. Its present composition may differ from the simple picture now being used. Inflation may require a new mechanism or may need to be replaced. The singularity may not have been a real event at all, but only a sign that humanity has reached the edge of its current map of physics. Beyond that boundary, history does not necessarily end. Space may once have contracted from an earlier era, reached an extreme state, and then opened again. The Big Bang would no longer be the moment when everything appeared, but the point at which the direction of cosmic evolution changed from contraction to expansion. From that possibility, the story begins to open into a far wider realm, where before the familiar hot and luminous phase, an entirely different universe may once have existed. Beyond the hot, dense phase recorded by ancient light and the light elements, cosmic history still contains a region that remains almost entirely unseen. Present equations can trace the expansion far back into the past, but as they approach the earliest state, matter becomes denser, temperatures rise, and familiar laws become increasingly difficult to apply with confidence. The map of physics gradually loses its clear outlines at the very place where humanity most wants to know what happened. In the story commonly told, every distance continues to shrink until the universe approaches a beginning of infinite density. Yet an infinite value appearing in an equation does not necessarily mean that nature once contained something truly infinite. It may instead be a sign that the method being used has reached its limit, just as a map ending at a coastline does not prove that nothing exists beyond the shore. From that boundary, another possibility begins to open. The universe may not have emerged from nothing, nor must it necessarily have begun in a state of zero size. Before the present era of expansion, it may have existed in a phase moving in the opposite direction, when the distances between regions of space were gradually decreasing. Instead of a path that simply began and then expanded forever, cosmic history may contain a very long period during which space itself was contracting. A contracting universe does not simply mean that every galaxy moves toward one point located in the middle of empty space. Just as expansion has no center, contraction does not require a common center either. Distances between widely separated regions decrease everywhere at once. Every galaxy cluster would see the others drawing closer, not because everything was rushing through a fixed space, but because the space separating them was becoming shorter. This image can be felt as a long breath of the universe itself. During the present era, space is opening, carrying galaxies farther and farther apart. In an earlier age, the motion may have proceeded in the opposite direction. Space slowly drew inward, moving very gently through most of that period, then contracting more rapidly as the density of matter increased. As large distances gradually decreased, regions of matter that had once been separated began approaching one another. Galaxies from the earlier era may have collided and merged. Large clusters drew closer to other clusters. The voids within the cosmic web were compressed, while radiation throughout space gained energy as its wavelengths became shorter. This is the reverse of what happens in an expanding universe. Today, ancient light continues to cool because its wavelengths are stretched along with space. In a contracting universe, the wavelengths of light would grow shorter over time, increasing the energy of the radiation. The more space contracted, the hotter the environment became, and structures that had once remained stable would gradually enter increasingly extreme conditions. During the early stages of contraction, galaxies might preserve their individual forms for an extremely long time. Their internal gravity would bind their stars tightly enough to resist the general motion of space. But as the overall density of the universe continued to rise, collisions between large systems would become increasingly frequent. Separate structures would gradually lose their boundaries, and matter would be drawn into an environment that became hotter and more uniform. Eventually, stars would no longer be able to maintain their familiar states. Gas between galaxies would be compressed and heated. Radiation would become more intense, and matter could be broken apart into smaller components. This process would not necessarily unfold as a perfect reverse playback of the present universe, because many natural changes cannot automatically run backward. Even so, the overall direction would remain clear. Density would increase, temperature would rise, and large structures would gradually be erased. According to general relativity, gravity is not merely a pulling force between objects. Matter and energy change the shape of space and time, while objects move according to that curved geometry. The theory describes planetary orbits, the bending of light, the motions of galaxies, black holes, and the expansion of the universe with great accuracy. When general relativity is used to follow a contracting universe, increasing density produces greater curvature in space. The equations continue carrying matter toward an ever more strongly compressed state. Eventually, they may produce a singularity, the name given to a boundary where density and curvature approach infinite values and the ordinary description ceases to function. The singularity should not be imagined as a tiny particle sitting within a dark, empty region. In a cosmological model, it is the boundary of all space. Every location approaches the same extreme state because the distances between regions are themselves shrinking. There is no place outside the universe where an observer could stand and watch everything being compressed into a single dot. General relativity, however, is a classical theory, meaning that it does not fully include the effects governing nature at the smallest scales. When matter is compressed to an extreme degree, those effects can no longer be ignored. This is where quantum physics enters the story. Quantum physics describes how particles and energy behave at extremely small scales. In that world, matter does not always possess a completely definite position and motion in the way large objects do. Physical fields are also never perfectly still, but always contain tiny fluctuations. These laws have been tested with remarkable precision in atoms, elementary particles, and many other microscopic processes. The difficulty appears when gravity becomes extremely strong within an extremely small region. General relativity describes gravity well, while quantum physics describes the microscopic world well. But the two frameworks have not yet been fully combined under every condition. A theory capable of unifying them is generally called quantum gravity, meaning a description of gravity in situations where quantum effects can no longer be neglected. Humanity does not yet possess a single theory of quantum gravity confirmed by observation. Even so, many lines of research suggest that the extreme state may differ from the singularity predicted by classical equations. When space is compressed to an extraordinarily small scale, its quantum structure may create an effect that resists further contraction. This effect would not resemble a hard wall already placed within space. It could arise from the way space and matter themselves behave at extremely high density. Under ordinary conditions, gravity draws matter closer together. Near the quantum limit, however, deeper laws may slow the contraction, bring it to a complete stop, and then turn it into expansion. The transition from contraction to expansion is called a cosmic bounce, or the Big Bounce. The name suggests a ball striking the ground and rebounding, but the universe does not collide with any external surface. The motion of space itself changes direction. Distances that had been decreasing reach a minimum value and then begin increasing again. From this perspective, the hot Big Bang does not disappear. It simply ceases to be the moment when everything was created. After the bounce, space expands rapidly. Matter and radiation exist in an extremely hot state, and the entire familiar history continues. Protons and neutrons combine into light nuclei. Atoms appear as the temperature falls. Ancient light is released, and fluctuations in matter gradually grow into galaxies. The Big Bang would then become the name for the hot phase that opened after this reversal. Instead of being the first page, it would lie between two eras. A universe that had once contracted before it, and an expanding universe that followed. The past would not end at the hottest state, but would continue into another branch of cosmic history. This idea resolves an important intuitive problem. The singularity of infinite density is replaced by a state that is extremely small but still finite. Temperature and density may become extraordinarily high, far beyond any conditions humanity has ever created, but they do not need to reach infinity. The equations would not necessarily have to end at a boundary where every prediction loses meaning. As appealing as the idea may be, the Big Bounce is not yet a confirmed conclusion. A model seeking to replace the singularity must do more than produce a reversal within its equations. It must show that matter, radiation, and the small fluctuations in space can pass through the extreme phase without producing results that contradict the universe we observe. The first difficulty concerns matter. During contraction, density rises continuously and structures are destroyed. When the bounce occurs, that state must transition into an expanding universe with the appropriate composition. The model must describe how energy is distributed, how particles appear, and why the post-bounce phase can become an almost uniform, extremely hot environment. This is not merely a question of whether matter survives intact. The atoms, stars, and galaxies of the earlier era almost certainly could not pass through in their former shapes. What might be carried forward are more fundamental quantities: energy, physical fields, certain fluctuations in space, or information preserved within the structure of the quantum state. The second difficulty lies in the original density fluctuations. Galaxies exist today because the primordial universe contained extremely small differences between denser and less dense regions. A Big Bounce model must explain where those fluctuations came from, how they changed during contraction, and how they were carried through the bounce. Some models propose that tiny fluctuations formed within the contracting universe and were then amplified as space shrank. The bounce transferred them into the expanding branch, where they became the seeds of later structure. This approach can produce features resembling those seen in the cosmic microwave background, but the result depends strongly on the type of matter dominating the contracting phase and on the mechanism responsible for the reversal. The fluctuations cannot be too large, because an early universe that was excessively chaotic would not produce a cosmic microwave background that is nearly uniform. Nor can they be too small, because galaxies would then struggle to form at the observed time. The model must generate just the right amount of variation while also preserving the correct distribution across many different scales. Another problem is that disorder may increase while the universe contracts. Small differences in the rate of contraction along different directions could grow, causing space to be compressed unevenly. Instead of approaching a smooth state, the universe might become increasingly distorted and complicated as it neared the bounce. We can imagine a room shrinking while each wall moves at a different speed. At first, the difference would be difficult to notice. As the room became smaller, however, the imbalance would become more pronounced, and its final shape would no longer be regular. In cosmology, this kind of uneven contraction could destroy the nearly flat and uniform state observed in the cosmic microwave background. Some models add a special phase of contraction to smooth out these differences. In those models, a form of energy with suitable properties causes contraction to proceed more slowly and uniformly while preventing geometric irregularities from growing too strongly. Yet that form of energy must be explained through reasonable physics and must not introduce new instabilities. Entropy creates another quiet question behind the bounce. Entropy is a quantity that describes the number of ways a system can arrange its components, and is often connected to the tendency of energy to spread out and of natural processes to resist being reversed. As stars burn, black holes form, and radiation disperses, the entropy of the universe increases. An earlier era containing countless stars and black holes might carry an enormous amount of entropy into the contracting phase. A big bounce model must explain what happens to all that complexity as space shrinks. Is it preserved, redistributed, or made irrelevant to the expanding branch? The answer still depends on the particular theoretical approach. Black holes present an especially difficult case. They are regions of intense gravity in which large amounts of matter are confined within a small volume. In a contracting universe, black holes could merge and become increasingly massive. Near the bounce, understanding how they interact with the universe as a whole would require a complete theory of quantum gravity, which does not yet exist. These difficulties do not make the Big Bounce a meaningless idea. They simply show that replacing a singularity with a bounce requires more than an elegant image. The model must be mathematically stable, avoid producing unreasonable quantities, and ultimately lead to a universe resembling the one humanity observes. Evidence capable of testing the Big Bounce may be hidden within the cosmic microwave background and gravitational waves. Gravitational waves are ripples in the structure of space and time, produced when massive objects move or when the universe undergoes powerful transformations. A contracting phase followed by a bounce could generate a background of waves with a different pattern from one created by inflation. Small differences in the temperature distribution of the cosmic microwave background may also preserve information about an earlier phase. These signals, however, are extremely difficult to measure and can easily be confused with random fluctuations. Humanity has only one sky to observe. We cannot create multiple universes and compare them as we would repeat experiments in a laboratory. The Big Bounce, therefore, remains in the region between serious physics and an unconfirmed possibility. It is not merely an imaginary story, because many researchers are building mathematical models and searching for observable signs. But it cannot yet be treated as the true history of the universe, because no evidence currently forces the data to favor a bounce over other explanations. The greatest value of the idea is that it changes the question. Instead of asking what emerged from nothing, researchers begin asking what state existed before the hot phase. Instead of treating the singularity as an answer, they view it as a sign that the present theory is not deep enough. The past is no longer blocked by an absolute wall, but becomes a region that may still be studied. Within this picture, the present universe is only one branch of a longer history. Every galaxy now moving away from us belongs to the expanding phase after the reversal. The cosmic microwave background is a trace of the hot environment that formed afterward. Hydrogen and helium were produced as the universe continued to cool, while the cosmic web grew from fluctuations that may carry part of a deeper history. No star or planet from the earlier era would need to survive intact for that past to leave a trace. A tiny difference in the cosmic microwave background, a distinctive form of gravitational wave, or a slightly different pattern in the distribution of matter could become a bridge between the two branches of the universe. The image of a long breath is therefore only a familiar way of sensing the idea. The universe has no lungs and does not inhale or exhale in a regular rhythm. But the transition from contraction to expansion suggests a process that did not begin with a sudden appearance, but with a change in direction within a history that already existed. Space may have contracted across a period far beyond any human timescale. Density increased, old structures gradually dissolved into a hotter environment, and the contraction slowed near a realm where classical physics could no longer provide an adequate description. From that extreme state, distances began to open again. A hot universe emerged, not as a birth from nothing, but as a dawn following the end of an earlier age. From this perspective, the Big Bang remains a profound event. It marks the boundary between two very different states, but not necessarily the boundary between existence and non-existence. Before it may lie a contracting branch, while after it lies the expanding space in which humanity exists today. A single bounce is not the final possibility. The transition from contraction to expansion may have happened only once in all of cosmic history. But it could also be part of a larger rhythm in which every period of expansion eventually leads to another phase of contraction. In that case, our Big Bang would be only one of many reversals, and the universe may have passed through so many cycles that there is no first beginning left to find. A single bounce could connect a contracting universe with an expanding one, but that idea still leaves a broader question. After space opens, stars and galaxies form, and enormous voids emerge, must expansion continue forever? Some models suggest that history does not end in a universe that grows colder and more diffuse. After an interval far beyond any familiar scale of time, space may reverse direction once again, begin to contract, and prepare the way for a new era. A history made of successive periods of expansion and contraction is commonly called a cyclic universe. Each cycle is a complete span of time, beginning in a hot state, passing through the formation of structure, and then approaching a transition into the next cycle. In this view, the Big Bang is no longer the single event at the beginning of time. It becomes one of many boundaries separating different eras of space. Not every cyclic model describes these cycles in the same way. Some propose that the universe expands, slows, contracts, and then bounces. Others use more complex physical processes to connect the extremely distant future of one era with the earliest state of the next. Even so, the simple image of contraction and expansion helps convey the central idea. Cosmic history may not be a straight path running only from beginning to end, but a repeating motion unfolding across spans of time that are almost impossible to imagine. The universe is expanding today, and that expansion appears to be accelerating. Galaxies that are not gravitationally bound to one another are moving increasingly farther apart. In the simple model most widely used today, the component called dark energy continues driving the expansion of space, so a future contraction does not arise naturally. A cyclic universe, therefore, requires an additional mechanism that is absent from the current model. Dark energy may change its properties in the extremely distant future. A physical field now driving expansion could gradually weaken or shift into a state that produces a different effect. The theory of gravity on the largest scales may also be more complicated than our present description. In models of this kind, accelerated expansion does not continue forever. After an immense period of time, it slows, and the distances between regions of space begin to decrease. This reversal would not necessarily occur as a sudden stop. No sound would travel through the universe, and no wall would appear to prevent galaxies from continuing to recede. The change could unfold very slowly. The expansion rate would decline across vast eras, approach an almost stationary state, and then turn into contraction. The motion of space as a whole would reverse, while gravitationally bound systems, such as galaxies and star systems, would initially continue to exist almost normally. As contraction became more pronounced, the distances between large structures would decrease. Galaxies once carried far apart would begin approaching one another on cosmic scales. The average density would rise, the wavelengths of light would shorten, and the temperature of radiation would gradually increase. Over an extremely long time, galaxies would collide more frequently, galaxy clusters would merge, and the vast voids within the cosmic web would slowly narrow. Familiar structures could not remain intact all the way to the most extreme state. As the environment became hotter and denser, the stars, planets, and galaxies of the previous cycle would gradually lose their individual forms. Matter would be returned to a simpler state, where high temperatures broke apart many structures that had formed over billions of years. Near the end of contraction, all of space might become hot and almost uniform, resembling a reversed version of the earliest stages of our present universe. A bounce would then carry space from contraction back into expansion. The temperature would remain extremely high, but the density would no longer continue toward infinity. Distances would begin opening again, matter would gradually cool, and a new sequence of cosmic history would unfold. Light nuclei would form, atoms would appear, radiation would separate from matter, and gravity would once again draw gas into denser regions where stars and galaxies could emerge. The galaxies of a new cycle would not need to resemble the galaxies of the previous one. They would form from new fluctuations in matter, pass through different mergers, and produce their own generations of stars. There is no reason for a planet, a star, or any complex structure from the earlier era to be recreated exactly. What repeats is not each individual object, but the larger motion of the universe from hot to cold, from uniformity to structure, and then back toward a denser state. A cyclic universe is therefore not necessarily a film replayed frame by frame. It is closer to the seasons passing over a landscape, where every year brings periods of warming and cooling, yet each cloud, leaf, and stream never returns to precisely the same place. The general laws may repeat, while the details of every cycle remain different. The most compelling aspect of this idea is that it weakens the need for a first moment. Every cycle has an earlier era before it, and that era connects to another cycle still farther in the past. When cosmic history is traced backward, humanity does not necessarily arrive at a point where everything emerged from nothing. Instead, there may be an extended sequence of contraction and expansion with no first cycle in the familiar sense. The image of an ocean makes this idea easier to feel. Across its surface, each wave rises and falls. One wave does not create the entire ocean, nor is it the absolute beginning of motion. It forms from the previous state of the water and passes energy into the waves that follow. Over a short interval, someone may choose one particular wave as the beginning of the story, but the sea itself had been moving long before that wave appeared. Although a cyclic universe offers a history without a single moment of creation, it faces a profound difficulty. That difficulty concerns entropy, a quantity commonly used to describe how widely energy has dispersed and how many possible arrangements are available to the components of a system. A state with concentrated energy and greater order generally has lower entropy. As energy spreads out and the system gains more possible arrangements, entropy increases. We can imagine a cup of hot water placed in a cool room. At first, heat is concentrated in the water, creating a clear difference between the cup and its surroundings. Over time, that heat spreads into the air until both temperatures become nearly equal. The energy has not disappeared, but it has become more dispersed and more difficult to gather again for useful work. The natural process moves from concentrated heat toward an even distribution. The water does not spontaneously draw heat from the room and become hot again. The tendency of entropy to increase gives time a clear direction. People remember the past, but not the future. A star gradually consumes its fuel, but does not collect the light it has already emitted and become young again. A shattered cup does not reassemble itself and leap back onto the table. All these processes move in the direction of greater energy, dispersal, and an increasing number of possible states. Within the universe, stars transform hydrogen into heavier elements and release radiation into space. Stellar explosions scatter matter. Light travels farther and loses energy as space expands. Black holes form from regions of strongly compressed matter and can contain enormous amounts of entropy. Across billions of years, all such processes increase the total entropy of the universe. A cycle that has lasted long enough, therefore, does not end in the same pristine condition in which it began. It carries with it the radiation already emitted, the black holes that have formed, matter that has been transformed, and energy dispersed across an enormous volume. When space contracts, this entire history does not automatically disappear. Density rises, but entropy remains and may continue increasing through collisions and other irreversible processes. This creates a problem for a sequence of identical cycles. After every period of contraction and expansion, entropy would be higher than it was before. The next cycle could not begin from exactly the same clean and uniform state as the previous one. It might contain more radiation, more complex structures, or require a larger volume to hold all the accumulated entropy. In early cyclic models, this buildup caused each cycle to become larger and longer than the one before it. When traced backward into the past, the cycles became progressively smaller and shorter, eventually still leading toward an initial boundary. In that case, cyclic history did not truly eliminate a beginning. It merely placed many additional cycles between the present and that boundary. A modern model must explain how entropy is handled before a new cycle begins. One possibility is that prolonged expansion spreads entropy across such an enormous volume that each region can begin the next cycle in a relatively smooth state. The total entropy does not decrease, but the entropy density within an observable region becomes extremely low. It is like diluting a quantity of ink into an ocean that continues growing larger. The ink still exists, but its concentration in any one place declines. Other approaches suggest that only a very small portion of the old universe enters the new cycle. Most black holes, radiation, and complex structures are left outside the region that develops into the next era. The new cycle would therefore not need to carry all the disorder of the past. Yet such a separation must be described through specific physical laws. It cannot simply be assumed that old traces naturally disappear. Black holes are especially difficult to handle because they contain such enormous entropy. In the extremely distant future, many stars will have gone dark, and much of the remaining matter may fall into black holes. These black holes gradually lose energy through an extraordinarily slow process, but the time required is vastly longer than the current age of the universe. A cyclic model must explain whether the next cycle begins before or after the black holes disappear, and what happens to the entropy they once contained. Beyond entropy, each cycle must also solve the problem of uniformity. A contracting phase tends to amplify some small differences. Regions contracting at slightly different rates can distort space. Matter left over from galaxies, black holes, and radiation also creates large irregularities. Yet the universe after the hot Big Bang appears to have begun in an extremely smooth state, carrying only fluctuations small enough to form galaxies later. Some models introduce a period of very slow contraction before the bounce. During that phase, a special form of energy gradually becomes dominant and reduces the relative influence of known uniform regions. Space is smoothed and flattened before reaching the extreme state. This mechanism could allow the new cycle to begin with conditions resembling those observed in the early universe, but the required form of energy and the way it operates remain among the parts that have not yet been confirmed. The transition through the bounce must also preserve the correct kind of primordial fluctuations. A completely smooth cycle would not be able to produce stars and galaxies. On the other hand, fluctuations that were too large would make the universe chaotic from an early stage. Small differences must appear with the right strength and distribution, then pass through the contraction and bounce phase without being destroyed or amplified too strongly. This is why a cyclic universe involves more than simply connecting many big bounces. Each cycle must prepare the conditions for the next, deal with entropy, smooth out irregularities, and recreate the appropriate fluctuations. A small deviation within one cycle could grow through repeated cycles until the history was no longer stable. The question of time also becomes more subtle. A cyclic universe may repeat the motions of expansion and contraction, but the direction in which entropy increases would still distinguish the past from the future. Time would not simply move forward during expansion and then reverse during contraction. Physical processes would continue in the direction of increasing entropy, so observers in a contracting universe would still experience time moving forward just as we do. Contraction is therefore not a film played backward. Extinguished stars would not relight themselves by drawing in the photons they had previously released. Ash and dust would not spontaneously become pristine fuel again, and galaxies that had collided would not separate along their original paths. Space would change direction, but the history unfolding within it would continue producing new states. This would give each cycle its own identity. A later cycle could be influenced by the one before it without repeating it. Certain fundamental properties might pass through the bounce, while most detailed structures would be destroyed. The connection between eras might survive only within extremely small fluctuations in the arrangement of space or in a faint background of gravitational waves. Gravitational waves are distortions that travel through the structure of space and time. They can be produced by massive objects moving violently or by transformations in the early universe. A period of contraction followed by a bounce could leave behind a wave background different from one produced during a phase of extremely rapid expansion. In principle, measuring the shape of that background could help distinguish a cyclic history from other models. The cosmic microwave background might also contain traces, because it is the earliest record of the present cycle carried to us directly by light. Certain patterns in its temperature distribution or polarization could reflect the way fluctuations passed through the bounce. However, the predicted signals are extremely faint and are often not unique to a single model. An unusual feature in the background radiation could come from a previous cycle, but it could also result from noise, matter lying between us and the ancient light, or simply a rare random fluctuation. So far, no observational evidence has forced scientists to conclude that the universe has passed through multiple cycles. Cyclic models continue to be studied because they offer a serious approach to the problem of the beginning, not because such a history has already been observed. They must continue to be tested against the cosmic microwave background, the formation of structure, gravitational waves, and every other trace of the early universe. Even without confirmation, the cyclic idea clarifies something important. The hot Big Bang does not necessarily represent the first appearance of space. It may simply be the opening state of the cycle in which we live. Before it may lie an era of contraction, and farther back still may be other periods of expansion and contraction, each carrying its own history. From this perspective, the age of roughly 13.8 billion years is not the age of all reality. It measures only the duration of the present expanding branch, from the initial hot phase to today. The complete history could be far longer, perhaps without any first boundary that humanity could identify. The present universe continues to expand. New stars are still forming, although more slowly than in the past. Galaxies continue to change, black holes continue consuming matter, and ancient light continues to cool. There is currently no direct observational sign that a future contraction is waiting ahead. A cyclic universe is therefore not a certain prediction of what will happen, but a possibility showing how deeper laws might create a history broader than the familiar model. An endless sequence of cycles creates the impression that the universe requires no first moment. But infinity does not automatically solve every problem. Entropy must be managed, contraction must remain stable, and every bounce must create suitable conditions. Until these questions receive answers supported by observation, the cyclic ocean remains within the misty realm of theory. Across that ocean, each Big Bang resembles a wave rising from a deeper motion in the water. It opens an era containing light, stars, and galaxies, then gradually falls as the old structures dissolve. No object remains unchanged through every wave, but the larger motion may continue from one age to the next. It is also possible that history does not require such violent periods of contraction and bouncing. Before the hot phase, the The universe may not have been shrinking, and the past may not be divided into many cycles. A quieter possibility suggests that the universe existed for an extremely long time in an almost stable state, without a clearly defined moment of birth. Only after a gradual transition did space begin to open and enter the hot era whose traces still surround us today. After considering images of a universe that contracted and then bounced, the past can seem as though it must always contain some enormous event. Space shrinks, density rises, old structures dissolve, and a reversal opens the way into a new era. But history does not necessarily have to pass through such a violent moment. There are quieter possibilities in which the universe did not burst outward from a first point and does not need to move endlessly through cycles of contraction and expansion. It may have existed for an extremely long time in an almost stable state before a gradual change carried space into an era of expansion. An almost stable state does not mean that everything is completely motionless. In nature, a system can preserve its overall form even while movement continues within it. A cloud can maintain its structure for a period of time even though its gas molecules are constantly colliding. A star can remain relatively stable in size even as its core continuously generates energy and its layers of gas remain in motion. Equilibrium is not absolute stillness, but a condition in which several different effects temporarily prevent the overall state from changing too quickly. An almost stable universe can be imagined in much the same way. The gravity of matter tends to draw space and its structures inward, while another form of energy may resist that contraction. The two influences remain nearly balanced, causing the overall size of the universe to change very little. Space still contains matter and energy, but it has not yet begun expanding at the rate observed today. The form of energy described in models like these is often represented by a physical field. A field is a property that exists at every location in space. The temperature inside a room can be viewed as a simple field because each point has a temperature value. The electric field surrounding a charge also exists throughout the nearby region and can affect other charges. In cosmology, a field can carry energy, change over time, and influence the way space expands. In the original state, such a field may have held the universe near equilibrium for an extremely long time. No external clock would be needed to determine how long that state lasted. Time would already be part of the universe's history, while stability would simply mean that its largest features changed very slowly as time passed. This picture does not describe empty space waiting for the Big Bang to appear. The universe already existed with its own space, matter, and energy fields. It simply had not yet entered the hot and rapidly expanding state recorded in the ancient evidence. The hot Big Bang came later, as a new phase within a history that had begun before it. That balance may have lasted for a very long time, but it did not necessarily have to remain forever. An almost stable state is often sensitive to small changes. The energy field could slowly shift away from its original value. The density of matter might change slightly. Extremely weak fluctuations that are always present in nature could accumulate until the balance could no longer be maintained. A fluctuation is a small variation around an average state. The surface of a lake may be nearly flat, yet still carry faint ripples. The air in a room may have a stable overall temperature, even though small regions are always slightly warmer or cooler than others. At extremely small scales, physical fields may contain similar fluctuations. Most are not strong enough to alter the overall state, but under the right conditions, a tiny variation can begin a much larger process. Once the balance of the universe was disturbed, space began to expand. At first, the motion may have been extremely slow, almost indistinguishable from the earlier state. Then the energy of the field drove expansion more strongly. The universe left its nearly stable era and entered a period of more rapid development before that energy was converted into particles and radiation. The conversion of energy into an environment filled with hot particles could have produced the state of the hot Big Bang. Space did not appear at that moment. It had already existed. What emerged was a hot, dense, radiation-filled era in which the first nuclear processes began. Hydrogen and helium formed, the temperature continued to fall, atoms appeared, and light was eventually able to travel freely through the universe. From this perspective, the age of about 13.8 billion years still has meaning for the hot, expanding history that humanity can observe. It describes the time from the very early stage of the hot universe to the present. But it does not necessarily measure the entire length of time the universe has existed. Before the hot era may lie a much longer history in which space remained nearly stable and changed so slowly that it left few clear traces. The Big Bang would then resemble dawn rather than the moment the sky itself was created. Dawn spreads light across the landscape and begins a new day, but the land existed throughout the night. In the same way, the hot phase may mark the moment when the universe entered the familiar state in which light, matter, and expansion evolved, while a quieter era had already existed for an immense span of time. This possibility is commonly described through the idea of an emergent universe. The word emergent does not mean that the universe came out of some place beneath space. It simply expresses the idea that the expanding state gradually arose from an earlier, nearly stable condition. It is like a current beginning to flow from the surface of a lake when the surrounding landscape changes, with new motion appearing, even though all the water did not come into existence at the same moment. This picture avoids part of the difficulty created by the singularity. The universe does not need to be compressed to infinite density because its history is not traced backward to zero size. Moving into the past, expansion slows and approaches a state with a finite scale. The equations do not necessarily end where temperature and density become infinite. An almost stable state in the past, however, brings its own difficulties. Gravitational balance is often hard to maintain. Even a slight disturbance could cause matter to begin collapsing or make space expand earlier than expected. A model must explain why the universe could remain in that condition for so long without collapsing, while still providing a natural path out of equilibrium and into the hot era. Another challenge concerns the density fluctuations that later produced galaxies. The original state must be uniform enough to explain why the cosmic microwave background appears nearly identical in every direction, yet it must also contain tiny differences from which gravity can build structure. These fluctuations must form and develop at the correct strength while the universe transitions from near stability into expansion. Not every version of this idea can overcome those challenges. Some models remain stable under certain conditions but are easily disrupted by another type of fluctuation. Others avoid the singularity but require forms of matter or energy that have never been observed. The emergent universe, therefore, remains an area of research, not a confirmed explanation of the history preceding the Big Bang. Despite the many questions that remain, this possibility shows that the beginning does not offer only two choices: emergence from nothing or a bounce from a contracting universe. Space may have existed in a very different state, remaining almost silent across an immense span of time before gradually entering an era of high temperatures, light, and developing structures. Yet even this view assumes that time extends backward into the past like a road. One could continue traveling along that road, through the hot phase, past the beginning of expansion, and into an even earlier era of near stability. Another line of thought asks a deeper question. Does time truly continue to exist in its familiar form as we approach the earliest boundary? In everyday life, time is often experienced as a flow independent of everything else. Things appear, change, and disappear within that flow. This way of thinking can make time seem like an invisible container that already existed, with the universe simply placed inside it at a particular moment. Modern physics connects time closely with space. The two are not entirely separate, but form a shared structure within which every event occurs. Mass and energy curve that structure. Motion and gravity affect the rate at which clocks pass. Time near an object with powerful gravity can move differently from time in a region where gravity is weaker. This shows that time is not merely an unchanging stage standing outside the universe. It is part of the universe itself, influenced by matter, energy, and the shape of space. When the entire universe approaches extreme conditions, the nature of time may change along with everything else. A question such as, what existed before the Big Bang, usually assumes that a timeline was already present on both sides. The Big Bang is placed on that line as a marker, and one only needs to look to the left to find the earlier period. But if time is part of the universe, this way of asking the question may no longer be appropriate at the earliest boundary. The North Pole is often used as an analogy for this idea. On the surface of Earth, a person can travel north from many different places. As they continue, lines of longitude gradually meet at the North Pole. Once they arrive, the question of which direction to travel to reach a place farther north no longer has an answer in the usual sense. The North Pole is not a wall hiding a secret land beyond it. It is the place where the concept of traveling north reaches its limit. In a similar way, time may reach a boundary where the concept of before no longer continues in the familiar sense. This does not prove that no deeper reality exists. It only suggests that the language of everyday time may be unable to describe that region. Asking what happened before the boundary may be like taking a direction that has meaning only on a familiar part of the map and attempting to extend it beyond the place where that direction is no longer defined. This comparison also has limits. Earth exists within three-dimensional space, so it is possible to stand outside the globe in imagination and view the North Pole from above. There is no evidence that humanity has any similar position outside time from which the whole of cosmic history could be observed. The universe does not necessarily exist inside a larger container, and its earliest boundary may not be a location that can be viewed from the outside. The important idea is that a boundary does not always need to have the same kind of region on both sides. A coastline marks the end of a map of the land, but it does not mean that all reality ends there. Beyond it lies the ocean, where symbols used to describe roads and fields are no longer appropriate. At the earliest boundary of the universe, concepts such as before, after, and duration may resemble the symbols of an old map, accurate within familiar territory, but unable to continue unchanged beyond it. Some approaches use quantum physics to describe this boundary. Quantum physics is the framework used to explain nature at extremely small scales, where particles and fields do not always possess completely definite values in the way large objects appear to. When quantum ideas are applied to the entire universe, space and time near the earliest state may no longer remain as clearly separated as they are in ordinary experience. Instead of a sharply defined moment when time suddenly switched on, the boundary may be smoother. The familiar direction of time could gradually emerge as the universe expanded and entered a state that could be described through classical laws. The deeper one moves toward the earliest region, the harder it may become to distinguish time from the dimensions of space. There is no need to imagine time literally turning into a spatial road that a person could walk along. This is simply one way mathematical models attempt to avoid a sharply cut endpoint. Instead of a timeline ending abruptly at a singularity, the structure of the universe may close smoothly, much as Earth's surface closes at the pole without requiring the edge of an abyss. Within this picture, the Big Bang still marks a profound boundary. It is the region where time begins acquiring properties similar to the time measured by human clocks, where the relationship between before and after becomes clearer, and where space enters its hot, expanding phase. But the boundary does not necessarily represent the moment when all reality was created from nothing. A still deeper possibility suggests that space and time may not be the most fundamental components of nature. A phenomenon is called emergent when it arises from the collective behavior of deeper components, even though no individual component possesses the full property by itself. Temperature is a familiar example. A single molecule does not have a temperature in the same sense that a cup of water does. The concept becomes useful only when a large number of molecules move together. A wave on the ocean is also an emergent phenomenon. Individual water molecules move only through small regions, but the coordinated motion of countless molecules creates a wave with its own shape and speed. The wave is real, can carry energy, and can strike the shore, even though it is not an object separate from the water. Space and time may emerge from a deeper structure in a similar way. The nature of that structure is not yet known and may resemble none of the familiar forms of matter. Only when many fundamental components interact might distance, direction, and the flow of time experienced by humanity begin to acquire meaning. Under ordinary conditions, space and time behave so consistently that they appear to be absolute foundations. But near the earliest boundary, the deeper structure may have existed in a state that had not yet produced a clearly defined geometry. As the universe changed, the concepts of distance and time may have emerged, much as the form of a wave appears from the collective movement of water. The question of what happened before the Big Bang would then need to be reformulated. Instead of searching for another era located along the same timeline, researchers might ask how the deeper structure transformed into space and time. Before would no longer be a position on a clock, but an incomplete way of referring to a state in which clocks and the very concept of time had not yet formed. This is a difficult idea to grasp because every human thought takes place within time. A sentence must begin before it ends. A memory belongs to the past. A plan points toward the future. Even when the mind tries to imagine a place without time, it quietly arranges its images into a sequence. A fully intuitive picture may therefore be impossible. Science often enters regions where everyday experience is no longer enough. An atom is not a miniature solar system. Light is not simply a wave or simply a particle. Curved space cannot always be imagined accurately as a two-dimensional sheet. Analogies help open the door, but beyond them lie deeper mathematical structures. The idea of emergent time has not been confirmed through observation. No measurement has directly shown that time is created from another, more fundamental layer. Different models offer explanations that are not entirely alike, and finding evidence that can test them remains an enormous challenge. Even so, this line of thought reminds us that the singularity in the equations does not necessarily mark the beginning of all existence. It may only be the place where our present language of space and time is no longer sufficient. A deeper reality may still exist, but it may not be describable as a simple sequence of minutes, years, or eras preceding the Big Bang. The two possibilities explored here lead to very different interpretations. In a nearly stable universe, time extends deeply into the past without a moment of creation. The hot Big Bang emerges after a quiet era. In the other view, time does not extend endlessly backward, yet it does not necessarily begin at a singularity either. It gradually acquires meaning as the universe emerges from a deeper quantum state. One view preserves the concept of before and extends it into the distant past. The other suggests that the word before itself gradually loses meaning near the earliest boundary. Neither has been confirmed as the truth, but both show that the story of cosmic origins is not limited to the image of an explosion occurring during the first second. The observable traces still begin with the hot phase. Hydrogen, helium, the cosmic microwave background, and the formation of galaxies do not directly reveal whether an earlier contracting universe, a stable state, or a realm without fully formed time came before it. They confirm only that, after that mysterious boundary, the universe passed through an extremely hot era and then gradually cooled. To distinguish among these possibilities, scientists must search for extremely small differences preserved within the cosmic microwave background, gravitational waves, or the distribution of the original fluctuations in matter. A nearly stable state might produce patterns different from those created by a bounce. A quantum boundary might also alter the probability of different types of universes appearing. But the signals are usually extremely weak, and many models can produce results that look almost the same. This uncertainty does not make the question less valuable. It shows that humanity is standing near the edge of its present map. Behind us lie regions that have been measured relatively clearly. Galaxies, the cosmic microwave background, the light elements, and the history of expansion. Ahead, the lines begin to fade because current physics can no longer continue drawing them reliably. At that shore, there may be an ancient landscape of time stretching deep into the past. Or beyond it may lie an ocean that cannot be described using the coordinates employed on land. The end of the map does not prove that reality ends. It only suggests that a new kind of map may need to be created. The Big Bang, therefore, no longer carries only the meaning of a beginning. It may be the dawn after an almost motionless era, the boundary where familiar time emerged, or the earliest phase that present laws can describe with relative clarity. Whichever possibility is correct, observable history still continues from that hot state to the galaxies shining today. The past may not contain a single moment of creation, but removing the first point does not make every question disappear. The universe still requires a mechanism to leave its former state, produce hot matter, and generate the tiny fluctuations that later became galaxies. Every explanation introduces new problems, and every model must ultimately return to the sky for comparison. While the past remains hidden beyond that uncertain boundary, the present universe continues moving forward. Distances between faraway galaxies are increasing, and expansion appears to be accelerating. What determines the future depends not only on how the universe began, but also on the component quietly acting upon space itself. That component is called dark energy. The name has appeared many times, yet its nature remains almost entirely unknown. It may keep the universe expanding forever, weaken with time, or change in a way that causes history to reverse direction once again. Whether the Big Bang was a beginning, a bounce, or merely the dawn after an immensely long era, the fate of space still lies within the mystery governing cosmic expansion today. The timeline of the universe does not extend only backward into a hidden past. It also opens forward, toward eras so distant that every star existing today will have faded into only the faintest trace. The Big Bang may have been an absolute beginning, a bounce between two cosmic ages, or a dawn emerging after an almost motionless state. But none of these possibilities alone determines what will happen at the end of history. The future depends far more on the way space is expanding and on the mysterious component now governing that motion. Throughout most of the universe's early history, expansion gradually slowed. Galaxies continued moving apart on large scales, but the gravity of matter constantly pulled against that motion, much like an object thrown upward continues rising while its speed decreases. At that time, each region of space contained more matter, so gravity was strong enough to reduce the rate of expansion. As space grew larger, matter became more thinly spread. A fixed amount of matter was distributed across an increasing volume, causing the average density to decline. Over billions of years, the slowing influence of matter weakened, while another effect began to emerge. Several billion years ago, expansion stopped slowing and began to accelerate. Very distant galaxies started separating from one another at an increasing rate as part of the overall motion of space. The still unknown cause behind this acceleration is called dark energy. The word dark does not describe its color, nor does it mean that it is a form of black material lying between galaxies. The name simply reflects the fact that the source of the phenomenon remains hidden. Astronomers can observe its influence in the changing distances across the universe, but they have not yet identified its deeper nature directly. Dark energy should not be imagined as a wind blowing galaxies apart. Galaxies are not necessarily being pushed through a fixed emptiness. Instead, the spatial distance between widely separated systems is increasing, and that increase is becoming faster. On smaller scales, gravity and other forces remain strong enough to hold matter together. The Milky Way is not being stretched apart star by cosmic expansion. The solar system is not growing with the universe either, because the sun's gravity holds the planets in their orbits. Objects on Earth are bound together by electrical forces between atoms, which are enormously stronger than the effect of expansion. Cosmic acceleration becomes noticeable only across immense distances, where galaxies and galaxy clusters are no longer gravitationally bound into the same system. In the simplest model, dark energy is associated with space itself. Every region of space carries an almost constant amount of energy density, even as the universe continues expanding. This description is called the cosmological constant. The word constant means that its properties do not change over time. A given volume of space today contains the same density of dark energy as an equal volume would contain in another era. Ordinary matter becomes more dilute as the universe expands. Dark energy in the form of a cosmological constant does not thin out in the same way. As a result, the more space expands, the more dominant this component becomes compared with matter. The acceleration does not need to become dramatically stronger over a short interval, but it continues, carrying unbound regions increasingly farther apart. The future in this model unfolds very slowly. There is no single moment when the universe suddenly ends. Major changes are spread across spans of time far longer than the universe's present age. Distant galaxies continue to recede, while their light is stretched to longer wavelengths and gradually weakens. Over time, many galaxies pass beyond the range from which signals emitted in the future could ever reach us. This limit is called the cosmic horizon. It is not a physical wall surrounding the observer, but a boundary created by expansion. Light always moves at the speed of light through its local region of space, but the space between the source and the observer can expand so rapidly that the signal never crosses the entire distance, which continues growing. After an unimaginably long time, galaxies beyond our nearby gravitational region would become fainter and eventually disappear from view. Observers in the distant future might see only the merged members of the local group, the small collection that includes the Milky Way, the Andromeda Galaxy, and many dwarf galaxies. The rest of the cosmic web would still exist far away, but new light from it would no longer be able to reach our region. The sky of that era would be far poorer than the sky we know today. This would not be because distant galaxies had been destroyed, but because distance and expansion had severed the possibility of exchanging signals. An observer living then might find it difficult to discover that the universe had once contained countless galaxies beyond their own system. The vast picture now revealed by modern telescopes would gradually close. Within the galaxies that remain gravitationally bound, stars would continue forming for a long time. Yet each generation of stars consumes part of the available cold gas, while explosions, radiation, and black hole activity heat some of the remaining gas or drive it away from star-forming regions. The supply of raw material gradually declines. Fewer new stars appear, while older stars reach the ends of their lives one after another. Massive stars burn rapidly and disappear first. Smaller stars consume their fuel much more slowly and may survive through extremely long eras. Eventually, even they fade. Galaxies gradually come to contain more stellar remnants than active sources of light. White dwarfs are the remaining cores of small stars. Neutron stars are dense objects formed after certain stellar explosions, and black holes hold matter within regions where gravity is so strong that light cannot escape after crossing their boundaries. The luminous age of the universe, therefore, does not last forever. When the final stars stop shining, space enters a darker era. Stellar remnants continue moving, colliding, or being captured by black holes, but familiar sources of light become increasingly rare. Across even greater spans of time, black holes themselves may slowly lose energy by emitting an extraordinarily faint form of radiation. The overall outcome is a universe that becomes progressively colder, darker, and more diffuse. Energy does not disappear, but becomes so widely dispersed that creating new complex processes becomes increasingly difficult. This state is commonly called heat death or the Big Freeze. The name does not mean the entire universe literally turns into ice. It refers to temperatures between regions becoming more equal, concentrated energy sources gradually being exhausted, and the capacity to perform physical work declining. This is the future most often associated with constant dark energy. The cosmological constant, however, is only the simplest description, not the proven nature of dark energy. New measurements are testing whether its influence has truly remained unchanged throughout cosmic history. To investigate this, astronomers examine several kinds of evidence. Extremely bright stellar explosions help compare distances across different eras. The distribution of millions of galaxies creates a three-dimensional map of space. Within that map lies a characteristic distance originating from ripples in the early universe, functioning like a ruler carried across billions of years of cosmic history. By observing this ancient ruler at many distances, scientists can measure the rate at which space expanded through time. The first 3 years of data from the DESI project strengthened a hint that dark energy may not be entirely constant. But the signal becomes clear only when several kinds of observations are combined, and its strength depends on which datasets are used. It is therefore not yet regarded as a certain discovery. This caution is important. A small signal may grow stronger as better data is collected, but it may also weaken or disappear once uncertainties are understood more fully. Early results do not show with certainty that dark energy is weakening, becoming stronger, or will reverse its effect in the future. They show only that the constant model is being tested with increasing precision. A component that changes over time is often imagined as an energy field. A physical field is a property that has a value everywhere in space and can vary with position or time. The temperature in a room is a familiar example of a quantity distributed through space, although a cosmic energy field would be far more fundamental and could not be felt directly like heat. Such a field might be changing so slowly that over a short era it appears almost constant. Across billions of years, however, a tiny change could accumulate and cause the expansion history to depart from the simplest model. The way the field evolves would determine the future, but present data does not yet reveal which path nature has chosen. If dark energy gradually weakened, its accelerating influence would become less powerful. Space might still continue expanding forever, but the acceleration would decline. Distant galaxies would continue separating, only at a different pace from the standard Big Freeze scenario. The cosmic horizon might develop differently, allowing a larger portion of space to remain capable of exchanging signals for a longer time. Weakening dark energy would not necessarily cause the universe to contract. To reverse expansion, the total slowing influence would need to become strong enough to overturn the overall motion. Dark energy fading toward nearly zero might simply leave a universe that continues expanding because of the momentum inherited from its earlier history, while matter becomes ever more dilute and no longer possesses enough gravitational influence to pull everything back together. Another path would make dark energy grow stronger as space expands. In that case, acceleration would not merely continue, but increase significantly. Distances between unbound galaxies would grow more rapidly, the observable horizon would shrink, and distant regions would disappear from communication sooner. The most extreme possibility appears when the density of dark energy increases without limit over time. This hypothetical form is often called phantom energy because its properties differ from those of familiar forms of matter and energy. Its effect on the expansion of space grows steadily stronger until it eventually overwhelms the forces holding structures together. At first, galaxy clusters are pulled apart. Later, smaller systems may also lose their gravitational bonds. As the influence continues to increase, it overcomes the gravity holding stars within galaxies, then the force keeping planets in orbit around their stars. Near the final moment in this model, even smaller structures are affected. This outcome is called the Big Rip. The Big Rip is not a general prediction of every model in which dark energy changes over time. It appears only in specific models where the density of this component increases rapidly enough and no mechanism brings that growth to an end. Present data does not allow scientists to conclude that such a future lies ahead. It is a theoretical limit that shows how sensitive the fate of the universe is to the properties of this still unknown component. Even in the Big Rip, expansion should not be imagined as an outside force pulling everything apart. The space between the parts of a system changes so rapidly that the binding forces can no longer preserve the structure. Yet this description lies far beyond anything that has been observed and depends on the assumption that this unusual form of energy continues behaving in the same way throughout the distant future. A completely different path opens if the influence of dark energy weakens dramatically and then changes its nature. The component that once drove expansion could lose its role or begin producing an effect that acts in the opposite direction. Once the overall inward pull becomes strong enough, expansion begins to slow. The universe would then resemble a river that once flowed quickly toward lower ground but gradually entered a region with a different landscape. The water would not reverse direction in a single instant. It would first slow down, the surface would become nearly still, and then the flow would begin moving in a new direction. In the universe, expansion could decrease over an extremely long period, approach zero, and then turn into contraction. As space began contracting, the densities of matter and radiation would rise. Distant galaxies would approach one another on large scales, collisions would become more frequent, and the temperature of the cosmic background radiation would gradually increase. Over a sufficiently long time, structures would lose their individual forms, and the universe would return to an increasingly hot, dense state. This collapsing outcome is called the Big Crunch. In classical general relativity, it could end at a singularity where density approaches infinity and the equations cease to function. A deeper theory might instead prevent contraction from reaching that limit, creating a bounce and opening a new period of expansion. The Big Crunch could therefore become a bridge connecting our present future with another big bounce. Cosmic history would then contain not only a contracting universe before the Big Bang, but possibly another contracting era in the future. However, this idea requires dark energy to change in a very specific way. With the positive, constant form used in the Standard Model, acceleration continues, and a universal contraction does not occur. The possibility that dark energy might change sign remains theoretical rather than observed. Here, changing sign means that its effect on expansion shifts from supporting growth to helping space contract. Such a process would require the energy field to move through different states, whose stability would need to be described by a complete physical theory. Between the Big Freeze, Big Rip, and Big Crunch lie many other possible paths. Dark energy might oscillate, gradually approach a new stable value, or interact with dark matter. Dark matter is the invisible component known through its gravitational effects. An exchange of energy between the two dark components could change the history of expansion in ways that would be difficult to detect through any single measurement. The variety of possibilities does not mean that every scenario is equally likely. A model in which dark energy remains nearly constant still agrees very well with most observations. Other possibilities are studied because small discrepancies have appeared in certain measurements, and because the nature of dark energy remains unknown. Science does not choose an ending according to how strange or compelling the story may sound, but according to how well the model agrees with the full body of evidence. This also clarifies the relationship between the beginning and the end. A universe that once passed through a big bounce is not required to contract again. A bounce in the past describes what happened at extremely high density, while the future depends on dark energy during the present era. After the bounce, space could still accelerate forever and move toward a cold, diffuse state. Conversely, a universe with a true beginning could still end in a big crunch. The fact that it appeared at an earliest boundary would not prevent dark energy from changing and gravity from regaining dominance later. The stories of the past and future involve related physics, but neither completely determines the other. A cyclic universe requires both ends to be connected. It must contain a mechanism that turns expansion into contraction, as well as another mechanism that prevents contraction from ending at a singularity. A single bounce in the past is not enough to create a cycle, and a future contraction alone does not guarantee that a new era will emerge. Each transition must be supported by laws capable of operating stably. A universe that emerged from an almost motionless state could also move toward many different futures. A quiet past does not guarantee a quiet future. After entering the hot phase and forming galaxies, its history would still be influenced by dark energy, just as it would in any other model consistent with the present universe. The question, was the Big Bang the beginning? therefore does not contain an answer to the universe's final fate. It concerns what may lie beyond the boundary of the past. Dark energy, meanwhile, determines the shape of the path opening ahead. These two mysteries stand at opposite ends of observable history, and humanity does not yet fully understand either one. The image of a river flowing toward land hidden beneath fog may help convey this idea. The stretches already traveled leave marks in the riverbed, revealing where the water came from and which landscapes it crossed. But the shape of the land ahead still determines whether the river will continue toward the sea, divide into several branches, slow within a broad lake, or turn in another direction along a different slope. The universe is currently moving along a path of accelerating expansion. Measurements reveal the present direction fairly clearly, but the landscape farther ahead remains unseen. Dark energy may be a permanent property of space, allowing the flow to continue forever. It may instead be an evolving field that changes the rate of expansion over immense eras. Humanity cannot wait billions of years to observe the entire process directly. Astronomers instead look deep into space, where light from different distances carries images of many different times. A distant galaxy is seen as it existed in the past, not as it exists now. By combining observations of millions of galaxies across many distances, scientists gradually reconstruct the history of expansion. Supernovae provide one way to measure distance. Patterns in the distribution of galaxies form another kind of ruler. The cosmic microwave background reveals the state of the young universe, while the bending of light by matter helps trace how structures have grown. Each method observes a different part of the story, and all must point toward the same history before a new model can be trusted. Evidence for changing dark energy would become convincing only if it appeared in several independent measurements. It would need to remain after instruments were calibrated more precisely, after the number of observed galaxies increased, and after different methods of analysis were compared. At the same time, the new model would still need to explain the cosmic microwave background, the ages of stars, the rate at which structure formed, and the measurements already matched by the current model. For now, the landscape ahead remains hidden in fog. A cold, diffuse ending is the simplest path suggested by the overall data, but it cannot yet be treated as the final answer. Hints from new maps remind us that dark energy may contain more change than the word constant once suggested. The future will therefore not be decided by the elegance of the Big Bounce, the endlessness of a cyclic universe, or the quietness of a beginningless state. It will be determined by the true properties of space, matter, and energy. Every possibility must leave behind a measurable difference, even if that difference is so small that millions of galaxies and many years of observation are required to reveal it. Behind us, ancient light still tells the story of a universe that was once hot. Ahead, dark energy is quietly shaping the part of history that has not yet happened. The path may continue forever into colder space, accelerate toward a violent limit, or slow and return to contraction. But until the evidence becomes clearer, the universe continues to keep its future hidden within a thin mist at the end of time. To discover which path is real, science cannot rely only on plausible endings written on paper. The Big Freeze, Big Rip, and Big Crunch must all be connected to what telescopes are measuring today. Each model must leave a distinctive mark in the history of expansion, in the way galaxies gather, and in the light that has traveled through space for billions of years. Those marks will carry the story into its next stage. Whether the mystery lies before the Big Bang or in a future concealed by dark energy, a possibility becomes science only when it leaves a signal that the real universe can confirm or rule out. A shoreline after the tide has gone out rarely preserves everything that happened there in perfect form. Deep footprints gradually lose their shape. Lines dragged through the sand are smoothed away, and small objects may be carried elsewhere by the waves. Even so, the beach seldom returns to exactly the way it was before anything passed across it. A faint depression, a layer of sand with a slightly different color, or a few stones displaced from their former positions may still reveal that the shore experienced an earlier movement. If a past before the hot Big Bang truly existed, it may have left traces in much the same way. Most of the large structures from an earlier era would be unlikely to survive intact through an extremely hot and dense phase. Galaxies, stars, and planets would not cross that boundary in their previous forms. But some more fundamental properties of space might be carried forward. Tiny differences in density, faint gravitational ripples, or the way primordial matter was distributed. Any such traces would have to be extremely subtle. Since the earliest phase, the universe has undergone nearly 13.8 billion years of expansion, star formation, galactic collisions, and chemical change. Every process has added another layer of history over the ancient signal. Searching for information from before the hot Big Bang is therefore not like reading a perfectly preserved document. It is more like recognizing a few old strokes of ink beneath many layers of writing placed over them. The first place scientists continue to search is the cosmic microwave background. This is the layer of light released when space became transparent, about 380,000 years after the initial hot phase. It does not directly illuminate a time before the Big Bang, but it carries the pattern of fluctuations in matter that existed even earlier. Whatever processes created those fluctuations may have influenced the way the temperature of the cosmic microwave background varies across the sky. Most of the structure within this ancient light agrees extremely well with the current model. Regions that are slightly warmer or cooler appear at sizes and strengths close to what is predicted for an early universe that was almost uniform. Those same ripples later grew into galaxies and the cosmic web. Yet when scientists examine the largest regions of the sky, a few features do not appear to fit the simplest pattern perfectly. At certain large scales, the temperature variations seem weaker than predicted. The two halves of the sky may also be somewhat less balanced than expected in a universe that is uniform in every direction. An unusually broad cold region and the alignment of several other large-scale patterns have been discussed for many years. Together, these features are often called large-scale anomalies in the cosmic microwave background. The word anomaly does not mean that a phenomenon has been proven to reveal new physics. It simply describes something that is somewhat unusual within the model being used. A fair coin can still land on the same side many times in a row. That outcome is uncommon, but it is not enough to conclude that the coin is defective. In the same way, a sky generated from random fluctuations can contain a few rare patterns without requiring an era before the Big Bang. The greatest difficulty is that humanity has only one sky to observe. We cannot create thousands of universes and compare how often each feature appears. In an ordinary experiment, repetition helps separate a genuine law from a random result. In cosmology, all large-scale information comes from a single case. This limitation is called cosmic variance. The term refers to an uncertainty that cannot be removed completely, because observers have only one version of the universe to measure. Even a perfect instrument, free of noise and capable of measuring every photon exactly, could not determine with certainty whether a very large pattern in the sky is evidence of deeper physics or simply a random form that our particular universe happened to take. The anomalies may also be influenced by nearer sources. Dust in the Milky Way emits microwave radiation. Gas, charged particles, and galaxies between us and the ancient light can alter the signal. Removing these foreground components requires observations at many wavelengths, because each kind of matter shines differently. Only when a feature remains after several independent cleaning methods does the possibility that it belongs to the early universe become more significant. So far, the large-scale patterns in the cosmic microwave background have not formed clear evidence of a phase before the Big Bang. Several features remain in the data, but the polarization of the light has not yet provided a sufficiently strong independent confirmation. Polarization describes how the directions of light's oscillations are arranged. Ordinary light can oscillate in many directions, but after traveling through or scattering under certain conditions, those directions can form organized patterns. The cosmic microwave background carries extremely weak polarization because its light was once scattered by electrons in the early universe. The arrangement of polarization directions across the sky contains additional information about the original fluctuations in matter. A feature that appears in both the temperature map and the polarization map would be more reliable than one visible in only a single type of data. It would be like two witnesses standing in different places but describing the same footprint on the shore. Polarization also opens a path toward another possible trace: primordial gravitational waves. Gravitational waves are ripples that propagate through the fabric of space and time itself. They are produced when large masses move violently, such as when two black holes orbit and merge. Waves of this kind have already been measured directly from events in the relatively nearby universe. The early universe may also have produced gravitational waves, but their sources would not necessarily have been individual black holes. A period of extremely rapid expansion, a bounce, or a change in the state of energy fields could have set the structure of space vibrating across many different scales. These ripples travel almost unhindered through matter, giving them the potential to carry information from eras that light could not pass through. Ancient light began traveling freely only after about 380,000 years, while gravitational waves may have crossed the dense environment far earlier. In that sense, they resemble an echo arriving from behind the fog that photons could not penetrate. Humanity does not hear them with the ear, but the extraordinarily small stretching and squeezing of distance can be detected with instruments or through the patterns they leave in the cosmic microwave background. Primordial gravitational waves could make the polarization of the cosmic microwave background swirl in a distinctive way. This swirling pattern is commonly called B-mode polarization. The letter B is simply a geometric classification, not a measure of intensity or a new kind of light. Instead of polarization directions radiating outward from or circling hot and cold regions in a simple pattern, they form structures with a twisting character across the sky. Finding this pattern with the expected shape would be a major advance. But the signal is extremely weak and can be imitated by several other sources. Dust in the Milky Way also produces polarization. In addition, as the cosmic microwave background travels toward Earth, the gravity of galaxies and dark matter bends its path. This gravitational lensing can convert part of the ordinary polarization pattern into a swirling form, obscuring any primordial signal. Seeing a B-mode pattern is therefore not enough to conclude that waves from the earliest era have been found. Scientists must separate the effects of dust, gravitational lensing, and other sources of noise. The remaining signal must appear across several regions of the sky, at multiple wavelengths, and in independent measurements. A well-known earlier claim of evidence for inflation weakened after the influence of Milky Way dust was evaluated more fully, showing why caution is essential when working with signals this faint. Not only the existence of gravitational waves, but also the way their energy is distributed across different scales is important. This distribution is usually called a spectrum. In everyday life, an audio spectrum reveals whether a piece of music contains more low notes or high notes. For gravitational waves, the spectrum shows how much energy is carried by long or short wavelengths. Each early cosmic history may create a different kind of spectrum. Some models of extremely rapid expansion produce more energy within a particular range of wavelengths. A contracting phase followed by a bounce may make other wavelengths more prominent. Phase transitions in physical fields may instead create a relatively distinct peak in the spectrum. A phase transition occurs when a system changes state after conditions such as temperature or density cross a threshold. Water freezing into ice is a familiar example. In the early universe, energy fields may have changed state as the temperature fell, releasing energy and producing expanding regions throughout space. Collisions between those regions could have generated gravitational waves. Because different sources leave different spectra, a gravitational wave background measured across many ranges could act like a fingerprint of the past. But no single detector can observe every kind of wave. Very long, intermediate, and short waves affect matter on different scales. Rather than focusing on the names of individual instruments, What matters is that several methods are gradually covering separate ranges of frequency, like nets with different mesh sizes being lowered into the same ocean. A signal appearing in only one frequency range could still come from sources that formed much later, such as countless pairs of black holes orbiting one another. To connect it with the early universe, the shape of the full spectrum must fit a specific mechanism without conflicting with the cosmic microwave background, the formation of the elements, or other observational limits. A correct explanation cannot match at only one point while failing everywhere else. Even if primordial gravitational waves are discovered, they may not point to only one possible history. Several models could create similar signals across part of the spectrum. Researchers would then need to search for subtler details: how strongly the waves depart from a random distribution, how they are related to density fluctuations, or whether different directions of oscillation behave differently. A footprint in the sand may reveal that something passed by, but it does not identify who it was. Its size, depth, the spacing between steps, and the surrounding marks must all be combined. Reading gravitational waves from the earliest era would be similar. The discovery itself would only open the door. The detailed shape would help identify the process that created them. While the cosmic microwave background and gravitational waves point toward extremely early times, the first galaxies tell the story of what came afterward. They do not look directly through the Big Bang, but they reveal how quickly the original seeds developed. A model of the past must lead to a universe capable of producing the right number of galaxies, the right kinds of stars, and the correct degree of matter concentration within the observed amount of time. The James Webb Space Telescope is extending this boundary by collecting infrared light from extremely distant galaxies. Infrared is light with wavelengths longer than the red light visible to the human eye. Light emitted by early galaxies was stretched by the expansion of space during its journey, so radiation that once lay in the visible range shifted into the infrared by the time it reached Earth. Some confirmed galaxies appear from a time when the universe was only a few 100 million years old. They show that stars, gas, and sometimes even black holes could gather relatively early. One galaxy observed as it existed about 280 million years after the hot Big Bang has pushed the visible boundary even farther into the past. Data like this does not automatically make the Big Bang model wrong, but it forces astronomers to test how quickly structure could have grown. The brightness of a galaxy does not directly reveal its total mass. Its light may come from extremely hot young stars, glowing gas, or matter spiraling around a black hole. A short burst of star formation can make a galaxy shine intensely, even if its total stellar mass is not especially large. Dust can also absorb certain wavelengths and re-emit the energy elsewhere, making the process of estimating mass more complicated. Images are therefore only the first step. The light must be separated into many wavelengths to form a spectrum. Every element absorbs or emits light at characteristic positions, like a set of identifying marks. From these patterns, astronomers can estimate distance, star formation rate, gas composition, and the possible presence of a black hole actively drawing in matter. Some objects initially believed to be extremely massive were revised after better spectra became available. Part of their light turned out to come from black holes or other processes, meaning their stellar masses had been overestimated. These revisions are a normal part of observational science. When a telescope enters a region that has never before been surveyed so deeply, the models used to interpret the data must also learn to adapt to unfamiliar environments. Even so, the earliest galaxies remain a valuable test. If their number and brightness continue to exceed every reasonable prediction, the description of structure formation will need to change. Primordial gas may form stars more efficiently. The first generations of stars may shine differently from nearby stars. Black holes may grow more rapidly. Dark matter may also possess properties that allow early gravitational concentrations to appear more frequently. Dark matter is the component that emits no light but creates gravitational effects. In the current model, it forms invisible concentrations first, after which ordinary gas falls into them and produces stars. The way dark matter moves, gathers, or interacts with itself directly affects the number of small structures in the young universe. The first galaxies, therefore, tell us not only about stars, but also indirectly test the unseen component forming their gravitational framework. A change in dark matter would still not necessarily imply an era before the Big Bang. It might only revise the way structures grew after the hot phase. This is why each clue must be placed in its proper location. Early galaxies could result from the physics of star formation, black holes, dark matter, or the history of expansion. Only after nearer explanations are tested does the need to alter the deepest layer of cosmology become clear. In addition to examining individual galaxies, scientists measure how millions of galaxies are distributed through space. They are not scattered entirely at random, but gather into the filaments, clusters, and voids of the cosmic web. Three-dimensional maps of this network record both distance and position in the sky, allowing the history of expansion to be followed across many eras. Within this distribution lies a characteristic distance that originated in waves once traveling through the hot plasma of the early universe. Plasma is a state of matter in which electrons are not yet bound to nuclei, creating a mixture of charged particles. Before atoms formed, radiation pressure and gravity caused matter to oscillate, leaving behind a preferred scale in the later distribution of galaxies. This distance acts like an ancient ruler. Its true size is inferred from the physics of the early universe, while its observed size at different eras depends on how much space has expanded. Comparing the ruler across different depths allows scientists to measure how the expansion rate changed over time. DESI is a project using the light from millions of galaxies and distant sources to build maps of this kind. What matters is not the instrument itself, but the breadth of the observational sample. A single galaxy has its own motion and complicated history. When millions are placed together, random movements fade into the background, and the common pattern of expansion becomes clearer. These maps help test whether dark energy is truly constant. An unchanging component produces one particular expansion history. An evolving energy field causes distances at different eras to deviate slightly. The difference is extremely small, requiring a vast region of space and many kinds of galaxies to detect. Current data has produced a hint that dark energy may change over time, but the evidence is not strong enough to close the question. The size of the discrepancy depends on how galaxy maps are combined with the cosmic microwave background and distant stellar explosions. This reveals an important feature of cosmology. Very few major conclusions rest on a single measurement standing alone. The cosmic microwave background reveals the initial conditions. Stellar explosions help measure distances in more recent eras. The cosmic web tracks both expansion and the way matter gathers. Gravitational waves may carry information from times inaccessible to light. The first galaxies test how quickly structures grew. Each piece of data has its own strengths and limits, but together they can make some models more compelling than others. Consistency among many parts is more important than one strange number. A new model may resolve the disagreement in the expansion rate while producing too much helium during the first few minutes. Another may allow galaxies to appear earlier, but distort the structure of the cosmic microwave background. An explanation of dark energy may fit galaxy maps while making the ages of ancient stars greater than the age of the universe predicted by the model. Every time one part is changed, the entire system must be tested again. This is why an intriguing signal does not immediately cause the standard model to collapse. Modern cosmology resembles a network of measurements woven together. Pulling one thread can shift many others, and a new theory remains strong only if the full network continues to hold the correct shape. The search for traces from before the Big Bang also faces the problem that many models can produce nearly identical outcomes. A subtle pattern in the cosmic microwave background might come from inflation, from a bounce, or from unknown initial conditions. A gravitational wave background might be created by phase transitions, networks of ancient objects, or countless sources that formed much later. Early galaxies might reflect new matter, but could also show only that star formation occurred more rapidly than expected. To distinguish among them, science looks for signals that differ not only in strength, but also in their relationships. One kind of gravitational wave may accompany a specific polarization pattern. A bounce may alter large-scale fluctuations in a way connected to smaller ones. Changing dark energy must affect both expansion and the rate at which structure grows. When several signals are linked in exactly the predicted way, the chance that they are merely coincidental becomes smaller. Independent repetition is also essential. Two teams using different instruments, regions of the sky, or processing methods, but obtaining the same result inspire far greater confidence. By contrast, a signal appearing in only one type of analysis may arise from a data choice or a small unnoticed error. Science advances slowly in these regions, not because ideas are lacking, but because the traces are so weak and the consequences of a false conclusion are so large. A claim about an era before the Big Bang would transform humanity's understanding of the origin of space and time. It would require more than one unusual cold region in the sky or a surprisingly bright galaxy. The evidence would need to survive new tests, remain consistent with the rest of the universe, and be explained more naturally by the new model than by the old one. Even if such a signal appeared, it might not allow the entire earlier era to be reconstructed. Footprints on a beach do not reveal the color of someone's clothing, the purpose of the journey, or every path they traveled. They confirm only that movement occurred and may reveal a few simple characteristics. Cosmic traces might likewise reveal only that a contracting phase, a phase transition, or another state existed before the hot era, while most details remain beyond observation. Reality before the Big Bang may have been almost completely erased by the hot phase. High temperatures and rapid expansion could have destroyed many original structures. Only the longest fluctuations or the least interactive waves may have survived. This places a natural limit on what humanity can know, no matter how precise future instruments become. But a limit does not make every search useless. A single reliable trace would be enough to show that the Big Bang was not the final boundary. A polarization pattern, a gravitational wave spectrum, or an unexpected relationship among fluctuations in matter could extend cosmic history beyond the hot era. The Big Bang would still not disappear. Hydrogen and helium would still have formed during the first few minutes of the current branch of history. The cosmic microwave background would still have been released when the universe became transparent. Galaxies would still have grown from slightly denser regions. The new discovery would simply place this entire sequence after an earlier stage, like finding an older foundation beneath a building that is still standing. That is also the most difficult standard for any replacement model. It cannot merely add a mysterious era before the Big Bang and stop there. It must explain how that era led to the hot state, why the light elements have their observed proportions, why the cosmic microwave background is nearly uniform, and how small fluctuations became the cosmic web. A new theory must also clarify the unresolved details left by the current model. It may connect the two measurements of the expansion rate, explain the early appearance of galaxies, or reveal how dark energy evolves. But the more it explains, the more tests it must face. Every new success carries the risk of creating a contradiction elsewhere. Science, therefore, does not search for the strangest story, but for the one that appears least forced when compared with all the data. A good model must do more than adapt after observations have already appeared. It must also make new predictions clear enough that a future measurement could prove it wrong. The ability to be rejected is what makes a hypothesis scientific rather than merely an appealing story. The cosmic microwave background, gravitational waves, the first galaxies, and three-dimensional maps of space are very different paths, yet all point toward the same question. Does the present universe carry any memory from beyond the hot boundary? The answer may lie in a signal so small that it is still hidden within noise, or perhaps no trace has survived intact enough to be recognized. Across the shoreline of cosmic history, billions of years of change have passed like countless layers of waves. Most ancient footprints have been flattened. What remains are only the faintest depressions in the light, weak ripples through space, and the way galaxies gather over time. Each trace alone can be misunderstood, but when many traces point toward the same history, the shape of the earlier path may gradually emerge. One day, a sufficiently clear signal may reveal that the universe contracted before it expanded, once rested in an almost stable state, or emerged from a structure in which time did not yet possess its familiar meaning. It is also possible that increasingly precise data will continue strengthening the current model and narrowing the alternatives. Both outcomes have value because every measurement that eliminates a false path makes the map clearer. Whatever direction the answer takes, a new theory cannot abandon what the sky has already confirmed. It must preserve the ancient light, the light elements, the density fluctuations, and the entire cosmic web within one consistent story. Only then could an extremely faint footprint from before the Big Bang lead to a broader understanding of cosmic history. At the edge of an old map, people often find unnamed blank spaces, coastlines drawn with broken lines, or lands known only through the uncertain accounts of earlier travelers. When an expedition returns with better data, the map may need to change. A peninsula may be redrawn, an island moved to a different position, or a region once thought empty may turn out to contain an entire mountain range. But the new map cannot simply erase rivers, cities, and coastlines that have already been measured accurately. It has value only if it expands the unknown while preserving what has already been confirmed. Cosmology changes in much the same way. A new model does not become correct simply because it tells a more compelling story about what came before the Big Bang. It cannot merely replace the singularity with a bounce, extend the past into a cyclic sequence, or claim that time emerged from a deeper structure, and then consider the work complete. Every idea must return to the observed sky and explain the full set of traces the universe has left behind. The first fact that cannot be ignored is expansion. Light from most distant galaxies is stretched toward longer wavelengths as it travels through space. This effect is called redshift. It shows that the distances between regions not held together by gravity are increasing with time. A new theory of cosmic origins must explain why expansion occurs, what state it began from, and why its rate has changed across billions of years. It is not enough to say that the universe once contracted and then bounced. The model must also lead from that bounce to an expansion history consistent with the observed distances between galaxies. A universe that remained almost stable in the past must likewise explain how that equilibrium ended and became the motion measured today. The stories may begin differently, but every one of them must pass through the same present sky. The next trace is the cosmic microwave background, the layer of light that separated from matter when the universe was about 380,000 years old. Its average temperature has now fallen to only about 2.7 Kelvin, extremely close to absolute zero. More importantly, this light arrives from almost every direction, follows an extraordinarily pure thermal spectrum, and carries temperature fluctuations of only about 1 part in 100,000. An alternative model cannot treat the cosmic microwave background as a minor detail. It must produce a phase hot and dense enough for light to interact continuously with matter, then explain why neutral atoms formed and allowed photons to travel freely. The temperature of that light today must agree with the amount of expansion that has occurred, while the small ripples across the sky must have sizes and strengths close to what instruments have measured. A bouncing universe must show how fluctuations from the contracting phase passed through the bounce. A cyclic universe must explain why traces from earlier cycles did not make the cosmic microwave background of the present cycle excessively chaotic. A nearly stable state in the past must also generate ripples small enough to preserve the near uniformity of the sky, yet large enough for galaxies to form later. The cosmic microwave background is like an old photograph captured at very high resolution. Many stories can be proposed about what happened before the picture was taken, but every story must lead to the same face, lighting, and details already visible in the image. A change in the distant past that is too large could distort the entire picture, even if the original idea sounds natural. The chemical composition of the universe provides another test. During the first few minutes of the hot phase, protons and neutrons combine to form light atomic nuclei. Protons carry positive electric charge, while neutrons carry no charge. Both are found in the central part of an atom. From them, the universe produced mostly hydrogen, a smaller amount of helium, and traces of deuterium and lithium. The proportions of these light elements cannot be changed arbitrarily. Temperature, density, and the expansion rate during the first few minutes determined how quickly nuclear reactions occurred and how long they continued. If the universe expanded too quickly, the reactions would stop too soon. If it expanded too slowly, more nuclei would continue combining, producing an amount of helium inconsistent with observation. A new model must therefore pass through a relatively narrow window of conditions. It must create an environment that was hot, but not for too long, dense, but not excessively so, allowing hydrogen, helium, and deuterium to appear in the correct amounts. Extending history to a time before the Big Bang does not remove this requirement. On the contrary, the model must explain why the earlier state naturally led to the brief nuclear furnace recorded by the present universe. Lithium remains one area of incomplete agreement. Some ancient stars appear to contain less lithium than the simplest model predicts. Yet a new theory cannot solve only the lithium problem while producing the wrong amounts of hydrogen or helium. It must improve what remains uncertain while preserving the results that already fit. This is one of the common difficulties in revising a major model. Correcting one detail can accidentally damage many others. After the first few minutes and the release of the cosmic microwave background, the universe entered the long process of structure formation. Regions containing slightly more matter produced stronger gravity, drawing additional gas and matter inward. Across millions and then billions of years, tiny differences grew into gas clouds, stars, galaxies, galaxy clusters, and the long filaments of the cosmic web. That web is not a random picture. The relative positions of galaxies, the sizes of the voids, and the degree to which matter is concentrated all depend on the initial state and on the later expansion rate. A new model must produce not merely a universe containing galaxies, but one in which galaxies are distributed in a way close to what surveys observe. If the initial ripples were too weak, structures would grow too slowly, and many galaxies would not have formed by the time they are already seen. If the ripples were too strong, too many dense regions would appear, making the universe clumpier than it really is. The expansion history also affects this process because rapidly expanding space can separate matter before gravity has time to gather it. Every model of an era before the Big Bang must therefore pass through a narrow path between uniformity and diversity. The early universe must be smooth enough for the cosmic microwave background to look almost the same in every direction, yet it must still contain differences large enough for stars and galaxies to emerge. These are not separate requirements. They are two sides of the same history. The earliest galaxies now being observed by modern telescopes are making this test more demanding. Some systems were already shining when the universe was only a few 100 million years old, earlier and more brightly than many simple models once predicted. These observations may show that star formation was more efficient. Black holes grew faster, or dark matter concentrated in a slightly different way. A truly improved theory must explain that early appearance without producing too many galaxies at later times. It must also agree with the amount of light, the composition of gas, and the star formation rates measured afterward. A solution that makes every galaxy grow faster may fit the earliest era, but leave the mature universe containing far more structure than observation allows. The ages of ancient stars provide another simple but strict limit. A model cannot predict a universe younger than the oldest stars contained within it. Stellar ages are estimated from the amount of fuel already consumed, chemical composition, and the stage of evolution a star has reached. Every measurement carries uncertainty, but the full history of the universe must still be long enough for those stars to form, age, and arrive at the states we observe. Distances to remote stellar explosions offer an additional test. A supernova is an intense burst of light that occurs when certain stars reach the ends of their lives, or when a stellar remnant undergoes an unstable reaction. One type of supernova has a relatively consistent true brightness after calibration, allowing it to serve as a standard light source for measuring distance. Light from these explosions across many eras reveals that the expansion rate has changed over time. Expansion once slowed and later began accelerating. Any new model of dark energy or gravity must pass through these measured points rather than fitting only the expansion rate today. Alongside supernovae, millions of galaxies create enormous rulers extending across much of cosmic history. Their distribution preserves a characteristic distance that originated in ripples within the primordial plasma. Plasma is a state of matter in which electrons are not yet bound to nuclei, leaving the environment filled with freely moving charged particles. Waves that once traveled through this plasma later left a mark in the way galaxies gathered. This characteristic distance is observed at many eras to measure expansion. A new model must agree simultaneously with the cosmic microwave background in the distant past, the galaxy rulers across the middle of history, and supernovae during more recent times. The three kinds of evidence resemble milestones placed along a long road. A theoretical curve cannot pass through one marker and miss all the others. This explains why one discrepancy is not enough to bring down the standard model. The tension in the expansion rate is significant, because measurements from the nearby universe give a value near 73 kilometers per second per megaparsec, while the value inferred from the cosmic microwave background and the current model is near 67. But any explanation that brings those two numbers closer together must preserve the other observations. A new form of energy in the young universe could alter the value inferred from the cosmic microwave background. Yet it would also affect element formation, the sizes of the ripples, and the rate at which structures grew. A modification of gravity could adjust the expansion rate today, but it would still need to describe planetary orbits, the bending of light, and galactic motion accurately. Science, therefore, does not search for a patch that covers only one crack. A good model must explain why the crack appeared while the rest of the wall remained standing. The more problems a theory solves through one general principle, the more valuable it becomes. The more separate adjustments it requires for each observation, the more unnatural it appears. The history of science has passed through changes of this kind many times. For centuries, the laws of Isaac Newton described the motion of objects and gravity with extraordinary accuracy. In Newton's view, an object changes its motion when a force acts upon it, while every object with mass attracts every other. These laws explained planetary orbits, falling objects, and countless events in ordinary life. In the early 20th century, Albert Einstein introduced relativity. In this theory, gravity is not merely a pulling force between two objects, but appears when matter and energy curve space and time. The new description explained phenomena Newton could not fully account for, including the small but unusual motion in Mercury's orbit, the bending of light around massive objects, and the existence of gravitational waves. Relativity did not make Newton's laws disappear. A car moving along a road, a ball thrown upward, or most satellites orbiting Earth can still be calculated extremely accurately using Newtonian formulas. The difference becomes important only when speeds approach the speed of light. Gravity is extremely strong, or very high precision is required. Newton was therefore not simply wrong. His theory remains an excellent approximation contained within a broader framework. Einstein did not erase the old map, but extended it into regions where its lines had begun to deviate. A deeper theory of the Big Bang may work in the same way. The hot, dense phase would remain valid as a description under the appropriate conditions. The cosmic microwave background, the light elements, and the formation of galaxies would still belong to real history. What changes would be the part before that phase, or the component governing expansion afterward. The singularity may be replaced by a bounce, but once density falls, the new theory must return close to general relativity. A new energy field may explain dark energy, but during certain eras, it must produce results nearly identical to those of a cosmological constant. Dark matter may be more complicated than currently assumed, yet on large scales it must still generate the familiar cosmic web. This is called the correspondence limit of a theory. It means that the new model must reduce to the old one under the conditions where the old model already works well. A theory cannot produce a completely different universe in regions that have been measured precisely merely to gain an advantage in a region that remains unknown. A new theory must also make testable predictions. After an unusual observation appears, it is always possible to adjust a model until it fits known data. But explaining the past is less powerful than predicting what has not yet been measured. A bouncing universe model may predict a particular gravitational wave spectrum or a distinctive pattern in the cosmic microwave background. A universe that remained nearly stable in the past may produce a slightly different distribution of fluctuations. Evolving dark energy would cause the distances between galaxies to depart from the constant model according to a specific rule. When new observations are made, those predictions may prove correct or incorrect. The possibility of being proven wrong is an essential part of science. An idea that explains every result, no matter how the data changes, does not truly distinguish between possibilities. A strong model must accept risk. It states in advance what should appear and what must not appear. Each alternative model must also avoid relying too heavily on things that have never been observed. Adding a new energy field may solve one problem, but that field must have a reasonable physical basis and must not create new instabilities. A mechanism that makes the universe bounce must explain why it operates at exactly the required density. A process that removes entropy between cycles must follow clear laws rather than being inserted simply because the model requires a clean beginning. Simplicity in science does not mean that a theory must be easy to understand or contain few equations. It usually means that many different phenomena are explained through a small number of general principles. Einstein's theory of gravity has deep mathematical structure, but it rests on one central idea: matter and energy can change the shape of space and even the rate at which time passes. That idea unites many phenomena once treated as separate. A new theory of cosmic origins would need similar power. It would be more convincing if the same mechanism removed the singularity, generated the correct primordial ripples, and left a measurable signal in gravitational waves. By contrast, a model requiring one rule for the bounce, another for erasing entropy, and several additional adjustments merely to fit the cosmic microwave background would be difficult to regard as the final answer. This does not mean nature must be simple merely because humans prefer it that way. The universe may be complex. But when several models explain the data equally well, the one requiring fewer arbitrary assumptions is usually the more reasonable starting point. In the end, new observations rather than aesthetic preference will decide. A genuine breakthrough may come when one model accomplishes three things at once. It preserves the successes of the hot Big Bang, resolves one or more present inconsistencies, and predicts a new signal that future instruments can search for. At that point, the theory would not merely change the story of the past, but open a new observational program. For example, a model might explain why two methods of measuring the expansion rate disagree by introducing a component that once existed in the young universe. That same component might also leave a small change in the polarization of the cosmic microwave background and in the distribution of galaxies. If all three signals were observed independently, the explanation would be far stronger than one that merely adjusted a single number. Another model might show that the Big Bang resulted from a bounce. The same mechanism responsible for the bounce could also generate a distinctive gravitational wave signature, transfer the correct kind of density fluctuations into the expanding phase, and avoid producing excessive disorder. If future measurements found exactly that combination, the possibility that the universe once contracted and then expanded would become far more credible. There is no guarantee that one theory will solve every question. The Hubble tension may come from an unrecognized measurement error. Early galaxies may be explained through star formation rather than new physics. Dark energy may truly be constant, while the lithium problem may arise from the way ancient stars alter their internal composition. The present discrepancies do not necessarily share the same cause. Yet even if each problem is solved separately, the question of the earliest boundary will remain. General relativity still leads to a region where its equations lose descriptive power, and quantum physics has not yet been fully unified with gravity. A deeper theory is still required to understand extreme states, even if every present observational tension eventually disappears. When that theory appears, it may not take the form people now expect. The universe may not be cyclic, bouncing, or nearly motionless. Space and time may arise from components that do not yet have familiar names. The Big Bang may be a phase transition, a geometric boundary, or a phenomenon understandable only when our present concepts are placed inside a wider framework. However strange the answer may be, it must still return to the simple traces surrounding us. It must explain why the sky contains a layer of light at 2.7 Kelvin, why hydrogen is more abundant than helium, why galaxies gather into a web, and why the distances between faraway systems are increasing. A theory of an era before the Big Bang cannot live only in an untestable past. It must influence the present universe, even if the effect is extremely small. Without a bridge to observation, the story remains only one mathematical possibility among many. The Big Bang, therefore, does not face a simple choice between remaining or disappearing. The part describing a universe that was once hot and dense may remain intact within most deeper models. What may change is its position in the larger history. It may no longer be the first page. Before it may lie a contracting branch, an almost stable era, or a state in which the concept of time had not yet clearly emerged. But after crossing that boundary, the universe must still enter a hot phase, create the light elements, release the cosmic microwave background, and form structure. A new map may extend farther into the past and deeper into the nature of space. It may reveal regions that the old map never knew existed, yet the measured rivers, the visible mountain ranges, and the established coastlines must remain in their correct places. That is how a scientific theory truly replaces the one before it, not by erasing the entire picture, but by explaining why the old picture worked so well, showing where it began to lose accuracy, and placing all of its correct parts within a broader framework. One day, humanity may discover that the Big Bang was only a bounce, a boundary, or a phase within a much longer history. When that happens, what we know today will not become meaningless. Ancient light will keep its temperature, hydrogen and helium will still trace their origin to the first few minutes, and galaxies will still have grown from very small fluctuations. The Big Bang will not disappear from cosmic history. It will simply leave the position of the first page and become a chapter within a larger story, no longer required to carry the entire mystery of where everything began.